Now that I have the floor, I want to give a shout out to Kate and Liz and Molly, who've really done the heavy lift of putting this workshop together. So thanks to you guys for helping us pull this off, and thanks to all of our presenters for making it happen as well. This has been great so far, and looking forward to a great program today. We'll start off with a keynote from Tom, and then move into, after a quick break, move into our morning session, where we kind of split the program between some more California operators content, and then moving into hearing from some of our Colorado collaborators as well. And then this afternoon, after lunch, we move into the science program, where we have a trifecta of Desert Research Institute folks talking about all kinds of cool things they're doing with ASO data. And as Kate mentioned, this afternoon, starting at 2 p.m. Pacific, we'll have an open discussion format. So in addition to chiming in with your questions for each speaker, be thinking about questions you'd like to ask to help focus that discussion. We're keeping it a little bit more freestyle this year to accommodate things as they come up, or interesting topics as they come up during the program. So it's somewhat fitting that we have a split California and Colorado content program this morning, because like myself, Tom, our mostly fearless leader, has a split background with Colorado roots and a strong California connection and residency to this day. So a native of Fort Collins. He knows the Colorado mountains well, and is always peering over the shoulder of whatever we're doing as we're mapping the Colorado basins. And likewise in California, I'm always looking for my favorite spots in the Sierra. So I think we all know Tom pretty well by now, so I'm not going to try to embarrass him. I'll save that maybe for the discussion later today. But I think the main thing here is that, we're looking at a 10-year legacy now of this program starting at JPL. And I think it's an opportune time this year to be looking back on that legacy and what it means, giving us momentum for the future. So excited to hear what Tom has to say in that regard as we're growing this program. Take it away, Tom.
All right. Thanks, Jeff, and thanks for not embarrassing me. You have plenty of fodder for that. So I presented this yesterday, but I just want to do it again, and I added to it some of our values. The ASO mission statement is to provide high quality, timely, and accurate snow measurement modeling and runoff forecasts to empower the world's water managers to make the best possible use of our planet's precious water. And that really that's at the core of what we do. There are many other aspects and offshoots of what we're doing, but that sits front and center in our minds as to everything that we are doing for our main customers related to snowpack and water resources. And what really think distinguishes us has been that from the very beginning we've been underlain by physical foundations. I mean, we really come at this from as much of a physical background as we can. The innovation on the LiDAR side with Jeff in the work, and on the spectrometer side with Joe Boardman, who has been key to many of the successful imaging spectrometers, either airborne or spaceborne. And then the snowpack work by Kat and myself on energy balance and albedo and imaging spectroscopy. And then one of the important things for us in who we have on the team, including the hiring that we're doing right now, is really honesty and transparency. When we have bugs, when we have errors, when we have issues, we want to make sure that our customers know that. And we don't really think of them as customers, but more so as partners. And equity is a very important part of who we are, and it always has been. One of these days, I'm going to have us do a talk on equity at the ASO Workshop. I think it's really important just to show where we've been with that, and also to speak to others in the field. Okay, there. So I updated the image, but somehow I didn't update the snow albedo from the correct spectrometers. I thought I had updated that. These are high specs, visible through shortwave infrared imaging spectrometers, and so I'll speak to this in a little bit. But key to what we do is to map in particular the two most critical snow properties for forecasting runoff volume timing, and those are the snow water equivalent and the snow albedo. The snow water equivalent we get to through the snow depth measurements, and then the convolution with snow density from the snowpack modeling from iSnowBal, from M3 Works, and updates to those modeled fields from observations. The snow albedo we get to from the imaging spectrometers. We have a full measurement now across the reflected solar spectrum, and that allows us to have a far more accurate measurement of albedo. The reason we care about that is about 90 to 95% of the energy that goes to warming and melting snow comes from absorbed sunlight. So that is the key knob on snowmelt rates. And then the physical modeling is this snowpack process modeling that we've done from the very beginning with originally with Danny Marks's ARS team in Boise, and now with the M3 Works crew, which also did the technology transfer out of ARS, and they are fantastic partners of ours. And likewise, the last couple of years, we've added partnership with Dave Gotchis at NCAR on the WRF hydro modeling, its snowpack, and then flow routing. And you'll see both of those in tomorrow's presentations. We have the rapid turnaround, and this used to be 24 hours, but it was 24 hours when we really didn't have very many products, not nearly as much QA/QC going on, and not as many distillates of what we're doing, as well as interaction between the data pipelines. And so now we're at 48 to 72 hours, which continues to be a reasonable turnaround. But we're always looking for ways for that to be far more efficient and to bring that back to that rapid turnaround. The uncertainties, I think it's important for us to mention this often. So the uncertainty of snow depth measurement at 3 meter posting is unbiased approximately 5 centimeters. And when that's coarsened up to 50 meters, at which scale we then multiply by the snow density field, that uncertainty drops to less than a centimeter. On the base SWE, we're looking at 1 to 2% uncertainties, and that's in that mapping of that total basin SWE. And then the snow albedo is approximately 1%. So these are the kinds of uncertainties that you want to have for these physically based models that we're running that are really at that cutting edge. And I also showed this. This will be the last of, I think, the slides I showed yesterday. ASO is flight processing, modeling, and then the SAS visualization and analysis. And And in particular, across this top line, well, actually, let me go to this line here. So, so the products are fed directly to the water managers, the California Cooperative Snow Survey Program, the Colorado Water Conservation Board, the individual irrigation districts and water conservancy districts. But likewise, they're fed to DWR for assimilation, well, for updating, I should say right now, of the Bulletin 120 model, and likewise going to the river forecast centers, going to the CBRFC and the CNRFC. But the data are all freely available. But this is going into the modeling systems that are set up at the state and federal levels, to which so many decisions are legally tied. So it's absolutely critical that we make our products work well with those modeling frameworks. And of course, both of those, in the state of California and likewise river forecast centers, are also looking at innovation with new distributed models. They've been working on this for some years. And we are helping out with that as we can. But the foundational models that they have used for decades, they continue to be important underpinning for water management in the West. And so it remains, as I said, very important that we work with them on being able to update those models with our products. Across the top line, this is the, first of all, at the top, the M3 Works interaction. That is updating the iSnowBell model with snow depth, and then feeding back to us the snow density field, which then gives us a more accurate snow density field to ultimately have this water equivalent. Fortunately, the M3 Works team is working on a flow routing component. And then at the same time, we have started up, as I said, the partnership with NCAR, working on the WRF hydro modeling framework. And both of these are really important for us to have our end-to-end capacity, all the way from flight planning, flight processing of the data through to the modeling. Not everywhere on the planet to where we want to go has a DWR Bulletin 120, has a river forecast center. And so we're working to have that full end-to-end capacity to be able to meet the needs, not only of those around the world, but also local entities in the West who may want to supplement the state and federal forecasts. And then ultimately the analysis and visualization. This goes on in various forms. The top one here is the Esri component. And I wanted to also use this as the moment to let you know that some of you are going to be pulled into some beta testing of the data system that we're working on, and the visualization and analysis tools with Esri, our strategic partner from the very beginning of ASO Inc. All right. Now, as Jeff alluded to, this has been going on for a little over 10 years, but this is our 10th year of flying snow on. And we had our first flights in 2012. We actually did a partnership with the National Ecological Observatory Network and did some differencing of snow on data relative to some USGS DEMs. It was heartening, but it wasn't the kind of quality snow-free data sets that we're at now. But it showed us that this was going to work. And then our first snow-on flights came with NASA headquarters support, but actually also with California Department of Water Resources. I show that right here. And And that was the Tuolumne Basin in April of 2013, and then also the Uncompahgre Basin in Southwest Colorado. And the program really started to build then. We started getting funding support from the state of Colorado in 2015. The National Snow and Ice Data Center began archiving data and distributing those in 2015. We started work in the Swiss Alps in 2016, and started expanding dramatically in California in 2017. And through that time, there were discussions at JPL and NASA headquarters about whether, when and if it was going to make sense for this program to leave the nest and go out to a private entity. And in the fall of 2018, with enough successes and the amount of pull that there was, plus the fact that JPL was looking for office space and looking to see as many non-visible, non-NASA activities move out as they possibly could, it became abundantly clear that we needed to make that transition. So I announced that I was going to be leaving JPL to do this, and Kat Boorman, our lead scientist, was still at JPL and volunteered, I think unwittingly, to be the PI while I had to recuse myself. And she did a remarkable job and somehow managed to keep her hair, despite all of the stresses that created for her. But we all owe her a debt of gratitude for the efforts that she put in during that time, as well as the rest of the team in supporting her as PI. So in 2019, we transitioned to Airborne Snow Observatories Incorporated, and we are a benefit corporation. And what that means is that we have, we're incorporated in the state of Colorado, and we have constraints on the kinds of work that we can do. So it keeps us in the channel of water resources and snowpack measurements, water resources for the public benefit, and it's great to look at that often. And I think that that helps explain where we're coming from. We were all scientists. For the most part, scientists and engineers and computer scientists coming out of JPL, and the subcontractors likewise coming out of the program, and went into business with the mindset of, we're doing this for the public good. And that reminds me, going back to the beginning, I was recruited in 2010 to JPL, University of Utah, where I was a professor, to build what was an ASO, and then ultimately see that springboard to spaceborne. And the way that I saw that recruitment was really, it was an opportunity for our team to take advantage of the resources that were being offered, to create a resource for the community, for the scientific community, as well as the water resource community and the utility communities that we had been so involved with on other research sides. And we consider it to be that way to today. So our interactions with NRCS, with the Snow Tel, that is very much that we are to complement them. Likewise, the California Cooperative Snow Survey Program and the other entities around the world with whom we're working, and we're starting to build further programs internationally. So right away, we had the strategic partnership with M3 Works and with Esri. So Esri signed on with us and really helped to bring us along with resources at the very beginning. And 2020 was our first season as ASO Incorporated. Now, you may also remember that spring 2020 also saw something else going on around the world, and that was the pandemic. And we were not quite sure that we were even going to be able to fly. Having 2 pilots and 1 operator in a small confined space where it's very difficult to be 6 feet away from each other it had us rather concerned that we were not going to be able to fly that season. But with support from the state of California, we were shown to be essential services, and we were able to go ahead with that season. It was fairly pared down, but it happened, and we learned a lot, even in the growth of that season. Then, likewise, in the summer of 2020, we signed an MOU with NCAR for a strategic partnership on Wharf Hydro. And then late in 2020 came the omnibus bill that had the ASO specific federal and state legislation. It does have other components of snowpack in it, but ASO is one of the key components of that program, which is ongoing, and we should have an idea here soon. Actually, I think the program has we had the first year last year, which was based on initial funding, and the proposals are going to be going in for this coming year. But that was a really exciting step at the federal level to act on seed funding for projects around the West. And so we're going to see, this community that we're all a part of, are going to see the growth and see the improvement in forecasting and our knowledge of the snowpack to feed that. In 2022, we grew to multiple ASOs. We had 2 of our own pairs of LiDAR and spectrometers. And then we have our partnership with Quantum Spatial, which is NV5, parent company, flying for us. And likewise, this spring we added the VSWR imaging spectrometers, which was a huge step forward for us, not only in data quality, but also data volume. And so it has required a heavy lift on computing, given that we're moving from 72 bands with our original spectrometers to more than 500 bands of spectrometer data. And so the compute team has done a remarkable job with efficiencies in that processing, getting that all the way to the snow albedo products. And in 2022, we also had our first international implementation as ASO Incorporated, and with the work in Norway. And we're looking at, in the next couple of years, seeing more extensions in Europe and hopefully in South America. All right, finally, in 2023, we are seeing a market expansion in California and Colorado, as Dave described yesterday. I'll show here in a little bit. So we're really moving toward realizing that vision of implementing this around the world, where it's geopolitically feasible. All right, so I like going back and showing the first collect here. This was April 2nd, 2013. This was flying in the Twin Otter. This was our first snow water equivalent map. It took 51 flight lines to cover this basin, and 2 very long flights, and also some rather ugly graphics. Fortunately, we've gotten much better with that as well. But yeah, this is 10 years. This is the first of 10 years of collects in the Tuolumne Basin. And so we were all, other than being fatigued, we were also rather, in the season, we were also really excited and rather emotional about the fact that this was 10 years worth that we achieved this year. Now, this is what the program has looked like. This is the, on the left, from the Central Sierra down here and the Tuolumne down through the Kings, which we've been flying for a few years. We then, with support from the Department of Water Resources in California, as well as Bureau of Reclamation, we've added the Feather, the Yuba, the Truckee, and the Carson. And the Feather is a substantially larger basin than any of the other basins that we had flown previously. It's about 8,000 square kilometers, whereas the San Joaquin down here is about 3,900 square kilometers. And Kings likewise right around that same size. And so that created some learning opportunities, how to fuse all of the multiple flights that were required to get the Feather, but produced some fascinating data this year. And as Dave described, some enormously helpful data in the Feather to really have a tight understanding of that distribution. And then here on the right, we saw a substantial increase as well in the Colorado program. In addition to the Dolores and the Conejos, then and East River and the Taylor, we also added Windy Gap and Blue River, which we've been flying as well. And what we're going to see is that we're going to start filling in this map and moving a little bit north and a little bit east as well. Here's a map. This is from Andrew Schwartz in the State Water Project at DWR. This just shows the program in 2020, 2021, and then here in 2022. And then this is what's planned in 2023. So yet to come is the Trinity over here. And some of these basins, the McCallamy and the Cosumnes, and the Fresno, but those with the efforts of Dave Rosardo and Ramesh Gautam and others are going to be seen here in the coming years. Then looking at the Colorado programs I mentioned, we are working right now, literally right now, on the snow-free activities. So in these beige areas, and we've already picked up the Yampa, the Roaring Fork, and some of the other basins in here. And as I'll show in a second, the plane is actually up right now. And then the blue represents the areas where we already have conducted snow surveys. And this darker beige or brown is our existing snow-free. So we're really starting to see the underpinnings of a full Colorado program that'll be represented later today and with the upcoming talks. And that program is the CASM, the Colorado Airborne Snow Measurement Program. I want to say likewise how much we appreciate what this community has done to really build ahead of steam to see the implementation around Colorado. And as Jeff mentioned, I'm originally from Fort Collins, and so those basins, looks like soon we'll be flying those basins that I looked at as a boy. Really inspired me to go into snow. So I love it. All right, so the imaging spectrometers. So we have there are actually two spectrometers, a visible through near infrared spectrometer. It's a silicon detector, and that runs from about 350 nanometers to about 1,000 nanometers wavelength. And then right next to it is the SWIR, which is the shortwave infrared. And this runs from about 980 out to 2,500 nanometers. And then through post-processing, we bring these through together as single spectra, co-registered. And that's where another place where Joe Boardman's remarkable expertise on remote sensing and in particular imaging spectroscopy has come in to be enormously valuable. And it was also beautiful to listen to Joe exclaiming as he did analyses of our original data and subsequent data sets as to the quality of these imaging spectrometers that we're able to get in operational mode and have on every aircraft. It's a stunning data set. This shows some of the spectral reflectances. In our old spectrometers would only go out to about, let's see, right about right here. And we would lose the detail of this ice absorption feature and this ice absorption feature. And likewise, we would lose the capacity to look at the vegetation and soils in a far more detailed fashion. This just shows some of the results. This is from, I believe, the Dolores Basin and some of the heavy dust loading that the southern part of Colorado saw this year that really drove the albedos down here into the 30 to 35% range. And here then is the hypsometry of those snow albedos, the near IR spur, the band, and the visible. And the reason that we show those, not only for our research interest, is that the models, so iSnowball, WRF Hydro, are set up to take those particular albedos. That's something that we're working on this summer to see the proper assimilation of those albedos into the model to really be able to update the snowmelt rates. Micah Sandusky yesterday mentioned that they were seeing those issues in the feather from the black carbon distribution off of the burned trees, and that they had needed to do some updates in the albedo. Now with these imaging spectrometers, we'll have very accurate updates to the snow albedo across the landscape. So this is really critical in achieving what we're after. And what we're after really is this cutting edge constraint of the physically based distributed models. And this, one can argue this slide is what we are about. Starting out with the LiDAR and spectrometer mapping of the topography, the flow routing as well in basins, and then likewise the distribution of vegetation, not only where the trees are, but how tall they are, and what the canopy density is, and being able to use that to update the models or constrain a new model. And then once we run into fire scars, being able to update those as well, as we were discussing yesterday. And seeing that transition from these Landsat products and other satellite retrievals to those that allow us to have a proper quantification of the biomass and the structure of that biomass. And then by extension, we can carry that to updated radiation fields, as Jeff described. The ASO SWI is core as well within season, and the ASO albedo. And then we also, a unique feature that we're working on, not only the snow-covered area that we're using from Landsat and Sentinel to add an additional constraint to the model, but also this new wave of spaceborne imaging spectrometers that are coming. and I'm deeply involved with several of those right now. The NMAP from the German Space Agency, that is launched, collecting data. I wrote those snow cover algorithms for that. EMIT, which is on the International Space Station now, and actually this is EMIT data. Oops, these are EMIT data here from the Tian Shan in Kazakhstan. And then Prisma, which is from the Italian Space Agency, and then upcoming the NASA SBG imaging spectrometer, and CHIME from the European Space Agency. So we're really heading in that direction, and our cutting edge algorithms to analyze those data are also going to be useful for having a more up-to-date cadence. So not just relying on ASO albedos, but also having that satellite retrieval to give us that additional advantage on constraining albedo in the model. These ultimately then are being carried in to iSnowball, and then likewise into WRF Hydro, as well as into the other modeling frameworks that are out there that we're interacting with. Snow-free work is going on this week, and yesterday was up here above Boulder, and then today we've moved up. This is the St. Vrain, am I right, Jeff, that we're flying today?
Yeah, St. Vrain and Left Hand.
Great. So and Dan has made more progress than what I'm showing here. That was about an hour ago. But this is really exciting for being able to see this program expand in Colorado, and in particular here in the Front Range of Colorado. I think the next to last item is the glacier monitoring that we are doing. So this was a commitment that we made, and I've mentioned this before, but it's a commitment that we made from the very beginning that we will do snow-free flights of the glaciers in California. As we expand in our program, as is possible, the glaciers in areas where we work, to map what's functionally their demise, and to have that legacy data set for generations to come. And so this just shows the McClure and Lyell glaciers here. These were the glaciers that 150 years ago John Muir worked on and discovered that they actually were flowing glaciers. And that really helped him to convince people that the landforms of Yosemite were in fact driven by extensive glaciers and not by massive floods, et cetera. And this is a close-up of the Lyell Glacier. In the time that we've been measuring this, going back to 2012, this area right here, which goes to bedrock, has become exposed. So in 2012, this was covered with glacier ice, and no longer is it. This is the profile that you see marked here. And this is 2014 minus 2012, 2015, 2016, 2021. We actually do have 2020 as well. We just didn't have time to get those in here, but we'll be flying it again here in the next month. But you can see how tremendous the downwelling of these glaciers have been. That's 18 meters of surface drop during that decade that we've been doing this work. Okay, and the final thing is just I want to speak to a new partnership that we have. This is with Sea Trees, which is likewise a nonprofit org that, as their statement here is to track carbon in every tree on the planet and deliver geospatial data for enabling natural climate solutions at all scales. This is from this was started by Sasan Sachi, who's a colleague of ours at the Jet Propulsion Laboratory. We're going to be providing the LiDAR and spectrometer operations for them. And this comes at a very important time to be able to provide the measurements and the analyses that can reveal how effective and honest the carbon sequestration and carbon mitigation activities are around the globe. So for us, this is a really exciting partnership, and one that again goes to our roots of being physically based and public benefit. So I believe that's it, and I will stop talking, having gone over by 3 minutes.
We'll allow it.
Thank you.
Thanks, Tom. Always exciting, even though I'm aware of all of that stuff. It's great to see it all put together in that one narrative. Pretty stoked. We've got, let's see, forgot to look at the calendar before I came back on here. We have well, let's take a couple of questions for a few minutes here, and then we go into a quick break. I see one from Jeff Dozier in the Q&A. Do we want to, Jeff, do you want to ask your question? I guess we have to allow to talk. All right, hopefully that worked.
I hope it worked. Did it work? Okay. Yeah, my question is on the accuracy of the basin integrated SWE at being 1 to 2%. And right. The question is, how do you actually validate that? I understand, for the depth and for the albedo, you can validate those by, you have other measurements of the same quantities, and therefore I see how those are validated. Mm-hmm. The basin SWE, you don't really have an independent estimate.
Right.
So the question, how can you in fact demonstrate that very fine level of uncertainty?
So the uncertainty in the basin SWE. So as you mentioned, starting point is the snow depth, and so the snow depth is unbiased, and as we go from the 3 meter to 50 meter, then our uncertainties drop from the 5 centimeters to less than a centimeter, and less than a centimeter at the 50 meter posting unbiased. Then that accuracy is estimated based on the snow density field campaigns that we've had, and so you're absolutely right that that we have not had a comprehensive. We don't have a capacity to have a comprehensive validation of those. That's an estimate based on those field measurements.
But hence the value, right? There's no other way to measure this.
Right.
Yeah. Okay. So we should talk about another campaign that's going on next year, and where we might be able to, in a situation where we know what the depth is, we might be able to measure the density.
Right.
And that would be, because the problem with the campaign is it's hard to get, you can't cover the whole basin very well.
Right.
Yeah. So,
right.
Okay, we'll talk.
Yeah.
Right. Good.
Great. Thanks, Jeff. I'm not seeing any other questions or hands raised out there. So maybe the thing to do is thank you, Tom, and we'll move on to, well, I'll hand it off to Kate to keep us on schedule here.
Sure. Yeah. Why don't we take a quick break and reconvene at the top of the hour, and we'll dive into our next presentations. Thanks, Tom. Thanks, Liz. We'll give it another minute or two for everyone to filter back in, and then Jeff, I'll hand it over to you.
Good. All right, we'll get rolling here. Excited for this next round of talks. Starting now, we'll have 3 talks here. First 2 from a couple of California operations, and then transitioning into the Colorado perspective. So after the first 3 for this morning session, we'll take a quick break, and then 3 more talks from Colorado folks will take us into lunch. So I'd like to welcome Harrison Forrester with Hetch Hetchy Water and Power to talk about some of their work with ASO data and the Hetch Hetchy operation. Harrison, do we have you?
Okay.
There we go, looking good.
All right. Good morning, everyone. Happy to be talking with you all today about ASO applications for Hetch Hetchy Water and Power operations. I'm Harrison Forrester, part of the Hetch Hetchy Water and Power and Planning team based in Moccasin out in the foothills. I'm basically standing in for Reggie Walters today, and I'll do my best to represent his really remarkable work integrating ASO into our operations. And his work builds upon a whole lineage of people, including Roger Picklum, Bruce McGurk, Nick Welty, to a minimal extent myself, and Dr. Chris Graham. So we are all mostly aware of Hetch Hetchy Reservoir based in Yosemite National Park, directly east of the San Francisco Bay Area. Hetch Hetchy can store 360,000 acre feet of water on an average water year. 740,000 acre feet flows through it, and an average April through July period has 590,000 acre feet. So it's generally an undersized reservoir for the annual yield. With all that in mind, our reservoir management objectives are based on our policy of being a water first organization. So we are the primary water source for the SFPUC and about 2.7 million customers in the Bay Area. So our first priority is filling Hetch Hetchy every year and operating the dam safely while doing so. Power supply is our next priority. There are 2 powerhouses along that transmission path on the way to the Bay Area at Kirkwood Powerhouse and Moccasin Powerhouse. And we can generate additional generation through those powerhouses in surplus of what we're delivering to the city. And after we've achieved that objective, we get on to our ecosystem management objectives. So immediately downstream from Hetch Hetchy Reservoir is a place called Pupinot Valley. And that's sort of the focal point of the Upper Tuolumne River Ecosystem Program. So last year, Reggie shared with you some great results, highlighting the utility of ASO for optimizing our power planning. And today we're going to try to walk you through how we achieved some of our ecosystem management goals with the use of ASO data. So here on the left is a shot of April 1 survey, our snow survey route. Very warm conditions, runoff well underway. And we're in the third year of a drought and managed to get to a position where we were comfortable with, by May 13th, making a large UTREP release with peak flows of 5,000 CFS out of Shaughnessy Dam. So we'll try to tell that story here today. As was discussed yesterday, this was the 10th year of flights in the Upper Tuolumne. Flights above Hetch Hetchy began back in 2013, and last year included the full Tuolumne. We had 5 flights last year, and all of those were really beneficial. Many of you are aware of this plot. Here we're looking at Hetch Hetchy inflows against a multiple linear regression estimate based on ASO and future precip. And the black circles are the flights from this year. So continued strong relationship between ASO, future precipitation, and runoff into Hetch Hetchy. So I'll just move along here to the incorporation of the ASO data into our precipitation runoff modeling system model. So many of you are aware of the PRIMS model structure. It's a distributed model discretized by hydrologic response units, HRUs. One of the great things about it is it gives us flexibility to run various future weather scenarios through it and effectively bound available water for water and power planning. And it's calibrated to our observations of snowpack at the snow pillow network and stream flow. The ASO data, so this is ASO snow water equivalent data, is resampled at that HRU level from the raw products we get after each flight. Here's a brief schematic of the assimilation routine that Reggie has developed. So the model is spun up from an initial condition. It's run, it's saved. We compute the difference between the ASO SWE and the model SWE, where there are HRUs that have no snow cover. This box, false negative ancillary variable update. Reggie's developed a great routine looking at nearest neighbor values to correctly update ancillary variables like albedo. That update is restarted into the SWE state variable, and we continue onwards with the model run. Just another way of looking at what's going on there. Here's a time series of all the HRU SWE values in the Hetchy Basin through time, and then the ASO update. And this is an example from 2020, I believe. Once we've updated the model, then we can provide a variety of future weather scenarios and get a nice ensemble with an updated SWE state that we have higher confidence in. So a bit of the workflow for forecasting spill at Hetch Hetchy Reservoir that we would potentially use for a UTREP release. We go out, we measure snowpack manually via the snow surveys, as well as looking at the automated snow pillow network. And we estimate a range of future precipitation. Ideally, the direct snowpack measurements are happening coincident with ASO flights to boost our confidence of each of those ASO flights. Those are run through a variety of hydrologic models to get a range of inflows. We compare the different model outputs. PRIMS is one of our in-house models, along with our statistical model, the water supply forecast model, and we lean heavily on the CNRFC ensemble products as well. So all of those are compared, and of course we're seeking some consensus between these different model outputs. Once we've got a high enough degree of confidence in one of those, we're running that through an operational model. Here is just a plot looking at filling the reservoir and optimizing power generation. Once we achieve those things, what sort of spill volumes, what range of spill volumes should we expect given the forecast date? So back to the Upper Tuolumne River Ecosystem Program, the goals of this are to mitigate impacts of Hetch Hetchy Reservoir on the ecosystem downstream. There's a variety of ecological objectives, and those are determined on the volume of water available to be released from Hetch Hetchy. We were focused on flooding Pupanat Valley this year. It's an objective that requires more water and one that hadn't occurred since 2019. Here's a map of Pupanat Valley, and the various colors highlight the stream flow that has to be reached via releases from O'Shaughnessy to inundate those areas. So we had a general spread of potential releases. We found that that was sufficient to fill Pupanat Meadow, that northern lobe. And that was timed to maximize the impact of that inundation and avoid other negative impacts in the valley. So ASO ingestion into PRIMS really provided confidence in the lower bounds of our internal statistical AGA runoff forecast. And here's just a comparison of actual observed flows through April and July compared to our PRIMS ASO range and our internal WSFM range. So nice agreement in the lower end of those. And this is an April 1 forecast. Additionally, by the time we're getting into early May, the PRIMS ASO updated, as well as sort of an ancillary tool we use called an ASO regression forecast. That's the box plot on the right pane. So that is utilizing that regression that I showed early in the presentation and driving future weather through that. And the red dot there is a zero precipitation scenario. So we saw, again, increased confidence in the lower bounds of in this case, the comparison of the CNRFC ensemble volume. So by the time we're in early May, we're gaining increasing confidence at our minimum inflows. And this is a little bit of a different view, and this is looking at the ASO update to PRIMS, improving the PRIMS model performance. So the box plot on the left showing hindcast results, including this year's weather. So the inclusion of ASO brought our our hindcast performance for the year to quite close to the observed inflows for AJ. Another way of thinking about that, the observed AJ was 306,000 acre feet. That was roughly equivalent to a 57% exceedance member from our April 1 PRIMS forecast, and AJ precip was around a 60% exceedance. So encouraging results and evidence that in the upper Tuolumne above Hetch Hetchy, precip is a dominant control on future runoff, given that we have antecedent conditions that are fully saturated this year. We expected that, had higher confidence in it from our big wet events in the fall and in December. And importantly, where ASO comes in, that SWE is estimated accurately in the model. So back to our UTREP release. This is a planned hydrograph, a template hydrograph that utilizes about 40,000 acre feet of water. Here we're looking at the actual hydrograph and what we were able to achieve for a UTREP release. So releases ramped up and hit around 5,000 CFS. We were able to maintain a long sustained bench. We came down in our releases, and then some wet weather in June actually put us back on spill conditions. Here's another way of looking at from the perspective of actual storage in Hetch Hetchy. So we brought the reservoir up to 350,000 acre feet before we had sufficient comfort in near-term inflow forecasts and total volume forecasts to draft the reservoir by 10,000 acre feet, achieving that UTREP release, and then bringing the reservoir back up to spill conditions. And here's some photos immediately after the peak release on the left, desiccated pond, and 6 days later after our release had taken effect, inundating that pond and achieving that ecological objective. So shifting gears a little bit here, I just want to make one more plug for the importance of ASO to our program, and as part of that, the importance of observations and field validation. We really rely heavily on any sort of ground measurement that we can look at that's coincident with ASO flights. And we are working on getting hole by hole lat longs to hopefully make some nice comparisons when we have coincident flights with the surveys. So we are very appreciative of all the work that goes into those QA/QC reports that come out with the flights. And with that, I will open it up to any questions. Many thanks to the whole ASO team, M3 Works, DWR, our downstream partners at Turlock and Modesto Irrigation Districts, and USDA ARS.
Awesome. Thank you, Harrison. I like that you're punting all questions to Reggie's email address there. That's a pro move. Let's see. Any questions out there? Reminder, you can type your questions into the Q&A box, or just raise your hand with the little hand raise button down there, and we can let you ask a question verbally. Oh, Kate's got a question. Go for it, Kate.
I do too, but I also see some, I think Scott Fenema just raised his hand and I can't see who else. Scott.
Oh, yeah, and Stephen Ho. Scott, go for it.
Oh, we might have to.
Perfect. You all can hear me?
Yep.
Perfect. Thanks for your presentation. It's really cool seeing this ASO data integrated into the PRMS model. We were thinking about doing kind of the same track of integrating ASO into the PRMS model for the Truckee. what kind of lift was it? Like how difficult, how much development time did it take for you to be able to get the model to pause and adjust the snow values as you did?
So I'm going to punt that to Reggie Walters' contact. He did the lion's share of the work, and I can say as his office mate, it took several months of pretty concerted effort, and ultimately being able to incorporate the methods that the ARS team used to update Ice Snowball.
Okay, good to know. Perfect. I'll reach out to Reggie. Thank you.
But Harrison, if I understand right, though, it's being run operationally, though, right? So it's near real time with the updates.
Oh yeah, the development was what I was referring to.
Yeah. But
No,
once you're
Reggie's-
within season, it's there in a near real time fashion.
Yeah, this last year we were, essentially taking ASO data and trying to throw it at the wall like spaghetti, see what modeling platform we could use to integrate this data in, and PRMS was one of them. But yeah, building the platform out to be able to handle it, it's extensive. So yeah, no, it's good to know and see that it works. So it could be worth the investment, especially when it's improving your model results and your forecasts.
Awesome. Thanks, Scott. We'll take one more question from Stephen Ho.
Yeah, I just wanted to kind of refer back to your chart that have the months and the timing that you guys consider important. I find it very interesting just because, from like yesterday from Steve Hagen and my talk, our priority as to when the forecast is extremely crucial for us is obviously very different from you guys. Is there any or no, you mentioned that by May is when you guys start to be using it. Has there been any other pressure or uses for the earlier flights per se then in your area?
Yeah, absolutely. The early flights really kick off our preliminary planning efforts and do a lot to constrain what we think is in the realm of possibility for the year ahead.
Okay,
Generally
I guess
speaking.
yeah, okay.
Awesome.
Yeah.
All right.
Yeah, and just to chime in on that, as we all know, that first flight being as early as possible and updating the models as early as possible is really valuable.
Great. Thank you, Harrison. Really appreciate it. Excited to hear that result. I remember in real time last year when you guys announced you're going to be able to do the UTREP flow releases. That was surprising to us, given the basically horrible state of the snowpack all year. So pretty stoked to see this result. So thanks for sharing it with us. We will move on to our next surprise last minute addition to the calendar here. Thanks to Chad Moore from Bureau Reclamation and the San Joaquin Fish Recovery Program for stepping up to fill in our 1020 slot here. Thank you, Chad.
You're welcome.
And, go ahead and take it away. I think you should have full permissions there. Yeah, great. Looks good.
All right, excellent. Yeah, pinch hitting today, but happy to do so. Okay, so just to orient everyone to the local neighborhood, the San Joaquin is in the middle of this graphic that, I don't know, whatever color orange that is in the middle. Our neighbors to the north, you've just heard from today and earlier, Stephen Ho is in the Merced, that green color, Harrison in the yellow, both of which cover Yosemite National Park. And to the south of the San Joaquin is the Kings, the Cahuilla, and all of those watersheds are ASO watersheds. So the San Joaquin is sandwiched between just the most beautiful country in the Sierra Nevada here, and drains to the west. So in 2022, we had a very asymmetric water year, as many of you know. We had 4 atmospheric rivers that resulted in getting more than 75% of our precipitation before New Year's Day. So we thought we were heading into another wet year, but then the tap was turned off. We had our driest January and driest February on record, and then below normal March, April, May. So this is a sort of a messy graph here, but showing the plots of various snow models, whether it be CNRFC or the no risk. I think what's important to point out is just this step here. This was our first, the response of our first ASO flight. So the ASO surveys, all 4 of them are those blue diamonds in this graphic here. And you can see that Reclamation's consensus estimate, I'll go into a little bit more about what that is, but that's our own blending of the forecasts. Took a big drop, over a 20% drop there with that first ASO data. So one of 2 possibilities: either we really overestimated, or the models really overestimated the amount of precipitation that occurred in those December storms, or there was substantially more melt between, roughly the end of December and when our first ASO survey was. I tend to think it was because of overestimation of precipitation, but I don't think that's all of it. I do think there was some more rapid melt than anticipated. So one of the things that we use on the San Joaquin watershed to drive our consensus estimate is an in-house water budget model. We do not have a spatial model like many of our neighbors do, although we're looking forward to some of the advancements and very much looking to the future to see what we could potentially use. But for now, we use a basic statistic model with water budgets to take the ASO information, and then from that, we'll make a decision on, okay, we want to lean towards the DWR forecast, our state water forecast, or we want to lean towards the River Forecast Center or some of them. And so the heart of this water budget model is runoff efficiency. So we have about a 5-to-1 interannual precipitation difference. We have about a 4-to-1 difference in runoff efficiency from one year to another. So that efficiency is nearly as important as just how much water actually falls on the watershed. And when we plot runoff efficiency, we get, for the San Joaquin, this very characteristic curved shape here with a fair amount of scatter, where each incremental increase in water that is added to the watershed raises the efficiency rapidly, and then it tapers off and becomes asymptotic. In this curve, like 100% efficiency on this particular graph would be 88 on this graph, which just has to do with the size of the watershed. And we can further sort of describe our trajectory, our position along this curve by defining some additional curves. And so we have these hypothetical logistical growth curves that explain how runoff efficiency varies from low elevation to high elevation. So on the x-axis, we have elevation here. On the y-axis, we have runoff efficiency. So perfect 1.0 is at the top, 0 is at the bottom. And the idea is we start, the year. We say, okay, I think we're going to be about in this position. It's a median year. So we will adopt a curve and track how snow converts to runoff as it flows off the mountain, and then basically test our hypothetical curve on a weekly basis. It's really that simple. It has a couple other parameters that we can turn the dial, but it's pretty straightforward. And so ASO data is a really big part of this because it gives us a very narrow range of uncertainty about what the snowpack is. And as we go through the year, more and more of the runoff is derived less from future precipitation and more from in-place snowpack. And so knowing that in-place snowpack really helps us understand runoff efficiency. And so we had 4 ASO surveys. Here's the plots of 4 of them. And then of course we have our iSnowbound model that this year was produced by M3 Works, and which is great for sort of interleaving between our surveys. And so each pair of surveys, or a survey, ASO survey and a model result, for example, can tell us, excuse the dog, can tell us what, how much snow we lost, and then how much runoff was produced from that. Now, 2022, we noticed something interesting. So here we are looking at these ASO cone plots at the top. So this is, I love this figure. This is like looking down on a cone from above, and you're seeing sort of the snow depth and SWE on various aspects. And what you gather right away from these is that even by our first survey, we were losing a lot of snow on the south-facing slopes. And it just got thinner and thinner as we went on across our 4 surveys. Now, this is telling us SWE depth. This isn't telling us SWE volume. Remember, the watershed slopes to the west-southwest, so most of our aspects will be favoring that west-southwest side. So this isn't SWE volume on an aggregate basis, but it is telling us SWE depth. And this is more of an asymmetry than we've seen in previous years. The bottom plots are showing the SWE depth by elevation band. So again, you get this very characteristic sort of rising as you get to the 8, 9, 10,000 foot elevations, and then it tapers off as you get to the high country, which tends to be more windblown and a lot of wind distribution. And you can see this sort of change over time of the shape of this. And I think that there's a lot to be learned from this kind of characterization of the snowpack. It is by no means the same from year to year. We don't just paint the same amount of snow or paint the snow in the same places with sort of various depths. It really does change. And I think we found one of the reasons why. And that is in 2020, the watershed had a fairly large and intense fire, the Creek Fire, and it burned 39% of the watershed area, much of it at medium and high severity. High severity, there's just like nothing left. And so this dramatically changed our vegetation cover. We had a lot of tree mortality prior to this, and so those dead standing trees were essentially converted to carbon dioxide here. Including some elevations up to 8,000 and 9,000 feet, so some fairly high elevation burn. And so anecdotally, we can say that runoff from these areas, at least in 2022, appeared to be a little bit higher than pre-Creek Fire, perhaps due to soil hydrophobicity, perhaps due to just loss of evapotranspiration, reduced evapotranspiration. Soot may be a factor, but I think that the presence of the fire, whether it be sort of a direct loss of vegetation cover and shade, or from sort of soot in the vicinity that gets scattered throughout the watershed and decreases albedo, I think had a large part in having the watershed melt its south-facing slopes first. So we've had ASO surveys from 2017. Our water budget model performed very well from 2017 through 2020. The last 2 years, it has not performed very well. And I think what we're seeing is instead of the snowmelt sort of marching up the mountain in elevation bands, it's melting to a greater extent preferentially on south-facing slopes. So the first snowpack that you lose is south-facing, thinner soils, somewhat less runoff efficiencies, And then as you progress through the season, you're getting into the north-facing slopes of snowmelt, where it persists longer and so forth. So it's a more complicated story now that we have lost the sort of ameliorating effects of a good forest cover. It's been said before, I'll say it again. We won our first ASO surveys in January, maybe even sooner. We could probably hitch this trigger to a certain SWE depth, but waiting past January doesn't make any sense unless it's the most dire of drought years. I think sort of we all need to be sort of paying close attention to the characteristics of the snowpack, particularly the aspect, even the subtle nuances of elevation distribution can really matter in how water comes off the ground. And so that's something that I've come to appreciate more this particular year. We really like to have, again, a first survey in January, and then surveys, starting in a second survey in late February, and then on about a 3 to 4 week cadence would be ideal. 4 weeks allows us a good amount of time to develop a good sample of runoff in between, as well as overcoming any sort of errors or variation there is from one ASO survey to another. So that's really an ideal sort of pace or cadence. And then of course you can interleave that with ice snowmelt modeling. I wanted to do just a second thing today here is to talk a little bit about a forecast reanalysis. This is our forecast plots across the year. The National Weather Service River Forecast Center is a solid line, sort of a smooth solid line. Our DWR forecast as squares. And then on the right side, we've got our, those open circles are the reclamation consensus forecast. And you can see that sort of big swoop up as we thought we were in a wet year, and then the absolute dive, and then a stabilizing out. And I think this matrix is just to show you here. This is sort of what we do on a weekly basis. And on that second column there, you'll see our blending. So we'll say, okay, based on our runoff efficiency models, the experimental WRF hydro and other information, we want to weight the DWR model, say in the first example, 10%, the National Weather Service model, 90%. And so that 1090 weighting will produce a blended value. And then we can get a full suite of exceedances out of that. And so that's how we roll from 1 week to another. But now that the year is basically done, we can go back and say, what would have been the appropriate forecast at a given point. And the first thing we do to determine this is we look at what our forecast exceedances should have been. And this is an amazing graph here. So in October, from October 1 forward, we were basically at our 65th percent exceedance. But that bottomed out completely on January 1. We were at our driest situations. We were effectively at our 100% exceedance on January 1. So even a 99% exceedance would be expected to decline in January and February, which is really an astonishing number. And we can then reconstruct what a perfect forecast would be. We basically run this backwards through our runoff efficiency model. It's not totally precise, but it does give a good example of where we should have been at various points. And I think from this, what we can learn from the process is that, that the California Nevada River Forecast Center did a good job with taking that ASO data and nudging their own snowpack numbers. Each time there was an ASO survey, they nudged it and they nudged it down. And that ended up bringing the River Forecast Center runoff forecast in line with reality. Had they adopted the ASO values right off the bat, like Scott was showing on the Truckee Carson, we would have been too low in the San Joaquin. So for whatever reason, the western slope, the way the model was verified and built up, if we had just spliced in the ASO data, we would have ended up with too low a forecast. So that works in some watersheds, that's great. We're hoping now that we have 6 years of ASO data that we can we can start to think about retraining the river forecast model based on that, maybe run a separate instance of it. But that's sort of a pie in the sky idea. We sort of, reclamation overreacted a bit to the ASO data and seeing how little water came off the mountain at various increments through the year, in part because I don't think we appreciated this aspect influence with the southern slopes melting off sooner. So, but we figured that out as we went on, and by May, our forecast was within 1.5% of accurate at whatever forecast exceedance you choose. So we've had very good luck with the ASO data, running it through our homespun fairly simple models, and from 2017 through 2022, our May accuracy was within 4% every year. So we're pretty happy with that. I think that's all I have for everyone today.
Fantastic, Chad. That's really cool stuff. Thanks again for stepping in at the last minute here. I think the runoff efficiency model that you guys have built over the years, I think represents a really important operational and decision support case that really helps to bridge the pure empirical approach and to a lot of the other, or to the primary operational models that are out there. As Tom mentioned in his talk earlier, there a lot of our partners and stakeholders are bound in one way or another to the RFC and NRCS and E120 forecasts, and that's not going to change in the near term. And I think one thing that always pops to mind when I see your runoff efficiency curve work is that this is a really interesting way to add an interpretation lever to those other forecasts. And you guys call it a blending, but really to me conceptually it's a how can we use this ASO information to interpret those official forecasts. So I'm really curious to hear from our attendees either now or at other times how a similar approach might be able to be rolled out in other basins. A couple of hands up. So Pat was first.
You're muted, Pat.
Muted.
Chad, thanks again for the presentation. Really enjoyed that. Especially, I'll refer to them colloquially as your snow cones. I wonder if you factored in with that, or was it included in the model, the albedo components that are there, not just from deposition onto the snow, but with the fire area, the creek fire area, if you could see those components in any of that.
No, we don't have any way to deal with albedo directly. It's one of those qualitative factors that we sort of say, okay, well, let's imagine the snow has lower albedo. What do we think is going to happen? And so our process is based on a lightweight tool, this runoff efficiency tool, making a hypothetical assumption, which blends a lot of qualitative factors, like I said, and then updating it on a weekly basis. So we're going for sort of rapid update cycle of hydrology intelligence over some sort of higher end model that would be far more accurate, but perhaps would be more workload than we could accomplish in a short period of time.
Thank you.
On the other hand, Jeff.
Question.
Yeah, I just wanted to. I wanted to throw this in, Chad. I'm going to commandeer sharing real quick. So this is from a poster a few years back that Kat led. Over here on the left are Snow 17 SWE versus ASO SWE for Colorado basins, and then these are California basins. Unfortunately, the San Joaquin's not on here, but the Tuolumne Basin alone, so just above Hetch Hetchy, shows this relationship, and then you can see. Let's see. I'm trying to remember what CE is. At any rate,
it's Cherry Eleanor.
Oh, Cherry Eleanor, right, separately. All right, so if you look at the Tuolumne by itself above Hetchy, this relationship is substantially biased, and so I think one of the things that we need to deal with Snow 17, and we've seen this starting to appear in some of the Colorado Basin River Forecast Center analyses, is that some of Snow 17 analysis or modeling of snowpack is around reality. Sometimes it's off a little bit, and then they calibrate accordingly. And so that may have something to do with what was seen with the RFC update. And so this is a place where we need to put more effort in. And actually, Molly, who's joined our team as an intern, is working on these components as well. And then the other thing I just want to say was the CBRFC has for many years now been using my dust radiative forcing product, which is just change in albedo from MODIS to update, so to do a radiative forcing equivalent change in temperature to update melt rates. And so we might look at something along those lines to feed to you out of the albedo data, so that we could have some kind of proxy in there that could help out with the melt rates.
Yeah, exciting points. I wanted to throw out that hypsography of a particular basin is going to matter a lot. San Joaquin has a mean elevation of 7,200 and something, which is going to be much higher than, say, the Tahoe Parson basins. So just the geography of the watershed and the very elementary sort of 3 elevation bands that the Snow 17 uses, like below 5, 5 to 8, and 8 and above. That Snow 17 is so crude in its elevational treatment, it's going to have different effects depending on the hypsography of the basin.
Right.
Awesome. I see Matt Meadows has his hand up. I'm a little worried that we're running pretty far behind here, and we've got some folks with time constraints this afternoon. So, Matt, if you wouldn't mind typing into the Q&A, we can get to. There's a couple other comments and questions in the Q&A as well. So we'll move on. Thanks again, Chad. Great stuff as always, and appreciate the last minute pinch hit there. So we'll move on to our next pair of presenters. That's Taylor Winchell from Denver Water. He's a water resources engineer working in the climate change adaptation and water supply planning programs. And Erik Skeie, who's a special projects coordinator for the state of Colorado Water Conservation Board, and together form part of the planning committee for the stakeholder-led Colorado Airborne Snow Measurements Group. Taylor, let her rip.
Okay, thanks, Jeff. Let me get my slides loaded up here. 1 second. All right, just holler at me if those are not coming through. Let me get into presentation mode here. Working on a small laptop screen at the moment. Great, all right. Hey everybody, as Jeff said, my name is Taylor Winchell. I work in climate adaptation and water resource planning at Denver Water. And then I'll be giving this together with Erik Skeie, who's at the Colorado Water Conservation Board, which is our state water policy and planning agency. here in Colorado, and we're going to provide you some updates on the statewide program we've been working on developing here called the Colorado Airborne Snow Measurement, or CASM program. So just a bit of background on sort of how this came to be. It really started in the halls of our summer Colorado Water Congress, which is a big Colorado convening water conference every year here in Colorado. In 2019, in a previous world we used to live in, Denver Water had done their first ASO flights in that spring of 2019, and we found them to be extremely useful for our operations that year, and we actually adjusted our operations based on the ASO data. And so we told this story at that conference, and that really started a lot of hallway conversations of people, you know, saying, oh, we're interested in this too. And clearly it's of value, but then sort of the barrage of questions came about of, you know, well, how much does it cost, and when do you fly, and what do you actually get with the data, and how can we partner on this, things of this sort. So we sort of organized an informal group to start talking through some of these questions in 2019, 2020. And then in late 2020, we decided it would be useful to do more of a formal sort of planning process around how we could establish more of a statewide program. And so we applied for a state grant in 2020. We were awarded that grant in 2021. It was a $45,000 grant, and it was really focused on doing this planning project of how can we start establishing this statewide program. And again, just some more of the motivation behind that is at that point in 2019, 2020, ASO flights to date in Colorado had clearly added high value to water management, but really had been geographically scattered and sort of lacked consistency in Colorado. We didn't have any sort of program structure to it. So we developed this goal for our project that was sponsored by this grant, which was to develop and communicate a roadmap for creating an equitable and sustainable ASO flight program in Colorado that will benefit basins statewide in a diverse group of water stakeholders. And so with that, once the grant really came through, we formed the CASM program, which has these various sort of levels of organization here. So we have the planning team, which consists of representatives from Denver Water, the Colorado River District, the Colorado Water Conservation Board, Linker, which is a consultancy here in Colorado, ASO, Northern Water, and Dolores Water Conservancy District. And if you're familiar with Colorado, you know, you can see that the agencies on here really represent a broad swath of geographies throughout the state and different types of customers served. And then we also have a stakeholder work group, which is over 100 members, and we meet monthly. We've met monthly since about April 2021. And again, we've really tried to get a wide diversity of both sectors and geographies from throughout the state as part of that stakeholder work group. And then just this year, we started, organized by Erik, who will be on after me, our flight coordination committee. And so that's about a 25-member committee that has met weekly throughout the flight season to have the discussions around when and where we're flying throughout the state. And I should also say here that we communicated, especially early on and really started to figure this out. We had quite a few meetings with Dave Rosardo over in California there. And actually seeing your presentation yesterday, Dave, really made me realize that we haven't chatted in a little while. So you'll probably see an email from me coming through soon. But that was really helpful to share these similarities and differences across states and really be able to learn from each other and how we're building these programs in our respective states. So we've developed a 4-part vision through this planning project that we've completed. We actually completed that project in June 2021, and we have both a report and an executive summary from that project, which is available on our website, which is coloradosnow.org, and potentially someone in the audience can add those reports to the chat if you can track those down. So our vision here really focuses on the holistic nature of how we see this program developing. So first and foremost is really around water management and decision support applications, which is ensuring that improved snowpack measurements through ASO and improved water supply forecasts really empower better water management decisions moving forward. And then vision 2 is around hydroclimate science, which is that ensuring that the CHASM program contributes to the advancement of watershed sciences. And we're fortunate to have a really strong research community here in Colorado and have quite a few members from the research community as part of our work group. And then vision 3 is around program structure and cooperative management. And so we really see ultimately CHASM being co-led by CWCB, which again is the Colorado Water Conservation Board, staff with local stakeholders cooperating on flight decision-making and really leading the program subcommittees so that it gets both the state perspective and then maintains the grassroots guidance as well. And then around funding is really that a sustainable CHASM program will require consistent state and or federal funding. So it's been largely locally stakeholder funded up to this point with some additional state grants. And while that's been really helpful to kick things off and get case studies and show the interest and the value, we know that the program won't only, it's an unsustainable model for it to be only funded by local stakeholders moving forward. So we're working to figure out how we can tap into those larger state and or federal funding sources. In terms of the CHASM structure, I'm going to break this down a little more on the next slide, but this just really shows we've been thinking a lot about what this program as an overall structure will look like moving forward. And really, I want to focus in on kind of the 4 committees that were at the top there. So again, at the very top, that's CWCB statewide oversight to help guide the program and hopefully help with contracting and policy around the program. And then there'll be likely additional contractor support, both of course from ASO and doing flights, and then an additional contractor to help with program logistics and things of this sort. And then we have our CHASM stakeholder advisory committee, which is really that planning team that I showed earlier that meets more frequently and helps guide the overall direction of the program. And then beneath that is really these 4 stakeholder-led committees. So the water sector stakeholder group overall, which convenes this larger group of stakeholders, the flight planning logistics committee, again, which is what we just formed this year, the funding and advocacy committee, which is pretty self-explanatory, and then the research integrations committee. So earlier this year in 2022, CHASM was awarded a $1.9 million what's called a water plan grant, which is a statewide grant program that's actually partially funded by sports betting here in Colorado as of some legislation from, I believe, 2021, was that, or 2020? And so CHASM applied for, we were awarded this $1.9 million water plan grant. Notably, there were 37 letters of support that went into our application for this grant. And what we heard time and time again is this is just sort of unprecedented level of support for a water project in Colorado. And there are many letters included in those 37 from organizations that don't always agree on the same things. So we see this as something that folks really agree will add high value throughout the state of Colorado. That grant funding, together with some local stakeholder funding, helped fund 14 snow-on flights. And here's our map of Colorado here. The snow-on flights were conducted in those basins that are in blue there. And then it's also funding snow-free work. Tom talked about that earlier. And I have my next slide is on the updated snow-free work as well. But all of those light orange areas there are areas where this grant is funding snow-free flights in those watersheds. And then again, the dark orange areas are areas that already have snow-free data. And that work was literally being done this morning. I'm not actually sure if the plane's still in the air. I'm sure Jeff can let us know on that. But yeah, we were flying just this morning from that. And then it's also, this grant is funding further coordination of our chasm work group and some data workshops. And then we've also been working on a streamflow forecasting integration project, looking at both the challenges and opportunities of integrating ASO into different streamflow forecasting models, and then looking at how different models performed in the ASO basins that we flew this year. So again, this is the snow-free work that we're doing with the water plan grant. So the colorful basins there are the ones that are filled in with colors, are the ones that we've flown so far this fall with snow-free. And then the ones that are outlined are ones that are still to come. And so if you're familiar a bit with Colorado here, this is the northern Front Range. This is the upper South Platte Basin. This is the upper Arkansas, it's the Roaring Fork. This is the headwaters of the Colorado River right here. And then this is the upper Yampa and upper Elk. So really exciting to have those basins ready to fly starting next year. We also did some, what I thought was really cool work in partnership with the CBRFC, the Colorado Basin River Forecast Center this year, where they did really experimental forecasts of integrating the ASO data into their forecasting model. And so they have their official forecast there. If you're familiar with how these are laid out, they have the envelope that they produce, and the official forecasts are there in the purple spread. And then when we did do ASO flights, this is for the Taylor Park Reservoir Inflow Watershed, they produced an unofficial, just experimental forecast where they integrated the ASO data from those flights. And that's the blue that you see there. And the dotted line is what the actual seasonal observed cumulative runoff volume was. And so you can see that in this case, the ASO data did actually improve the forecast here. This is probably the best one we saw, so this is certainly cherry picked for this presentation, but I think we all know that there's a lot of work to be done to fully integrate this into these models in the long term, but I think this offers some promise for what's to come. And then some next steps for the chasm program. So one, we'll just be working to complete that water plan grant activities, the snow-free flights there. And then the further chasm coordination and the streamflow forecasting integration project continue to expand snow-free coverage. So there's still quite a bit of the state that does not, even after this grant, will not have snow-free coverage, and we'll need to track down more funding to make that happen. We'll be continuing to more formally explore integrating chasm into the Colorado Water Conservation Board. And then again, working to establish long-term sustainable funding sources. And then some of the challenges we really see moving forward. So one is on the contracting side. You know, right now contracting is really difficult for each basin, each flight. We're really needing separate contracts. And within these contracts, there are often multiple entities contributing funding to that. And this is really this is really a huge barrier for us as we're working to build out this program right now. And it's one of the potential big benefits we see with integrating this into a more central organizing body in the CWCB. And then what I'm calling the bridge funding years of the next couple of years, where again, we're trying to tap into these larger funding sources, but that's not happening immediately. And so being able to maintain momentum of the program through really local stakeholder funding, again, to like bridge us into those years when the larger funding sources come into play, is a big challenge for us. And it's proving challenging to tap into, especially some smaller stakeholders throughout the state. Big question for me that, you know, I'd love some more guidance on is how do we tap into federal funding? You know, there's from both the bipartisan infrastructure law and the Inflation Reduction Act, there's been about $12 billion allocated towards water resources management. And so the big question for me is how do we get that to fund more ASO work and ASO associated work? And then on the understanding and communicating ASO pricing, this is really kind of a favor to ask from the ASO team and community. I think for us that are really water stakeholders and are sort of de facto kind of ambassadors for and really believe in this technology and the value that it adds. The question that we most frequently get when we're talking about ASO to either larger groups or those in our organizations making funding decisions, or even the media is, well, why is it so expensive to do this? And the answer is often we're not really quite sure. And that leaves us pretty flat-footed in those conversations, and can often stall the conversations. And so to unstall those conversations, it would be really helpful to have some more communication on what's behind ASO pricing, and why it is expensive. And then on the carbon emissions side, you know, I think it's an unfortunate aspect of many climate adaptation approaches that they actually do end up emitting more carbon emissions at the end of the day. And, you know, I'm not sure how it all plays out in the wash with how ASO data actually might, you know, reduce emissions in some cases by leading to more hydropower production, things of this sort. But we know that flights add more emissions to the atmosphere, and that this is certainly communication challenge for us. Again, at our organizations, within the media, I've certainly seen comments on articles about ASO that are sort of lambasting it for adding more emissions to the atmosphere. So I think this is just a challenge that we all need to have the conversation around. And with that, I'm gonna pass it on to Erik Skeie at the CWCB. But if you'd like to get involved, again, you can check out our website there, which is coloradosnow.org, and you can feel free to reach out to myself or Erik at the CWCB there.
Awesome, thanks, Taylor. So as per usual, I don't have any kind of PowerPoint. I really wanted to talk about the history of ASO in Colorado. You know, yesterday Tom was talking about how it's a really exciting time right now to be involved in this kind of work, and maybe some of the newer folks don't quite get why it's so exciting. So I wanted to share a little bit of Colorado's history and why we're so excited, particularly for this chasm group and getting to expand this effort and really getting to see all of these presentations about the value of the ASO data, right? So like Taylor said, I'm with the Colorado Water Conservation Board. We're the state of Colorado's funding and water policy agency. And we're really a stakeholder-driven agency, and that's going to be important to this tale of Colorado ASO. And really, this all began for us back in 2014, 2015. My fellow snowbro, Andrew Rickard, and I run the program now, but before us was a gentleman by the name of Joe Busto. And back around this time, he was really a part of this effort to fill data gaps throughout Colorado. And there was a large effort going on down in the Rio Grande Basin, which I'm sure Craig Cotten is going to get into, called the Rio Snowflow Experiment. And we threw the kitchen sink at Craig Cotten and Dave Gotchis to try and get them better streamflow forecasting for compact administration. We were throwing temporary radars at them, snow light stations, weather stations, and this new thing we had just heard about, ASO data. We'd seen it implemented in California a couple times, but we were still a little unsure about whether or not it would have value up here in Colorado, especially for the cost. So we're like, well, let's give this a shot and see if it'll work out. And when the Rio Snowflow report came out, the ASO data hadn't been processed quite yet. But I can tell you, when we got that processed ASO data with the Wharf Hydro, Joe and I were excited. We were seeing this whole new opportunity of figuring out a way to get better streamflow forecasting for our stakeholders. And that was the overall mission of this entire project. So we're like, yes, this is awesome. Then we ran into funding problems. We tried to spread the good word of ASO throughout the state of Colorado. And as Taylor said, it was very inconsistent and geographically spotty. We had to figure out ways to incorporate this with other ongoing projects. So for the Conejos and Rio Grande, it was pretty easy to tack it onto the Rio Snowflow stuff. For the East and Taylor River basins, we used the ASO data to support Kenneth Hurst Williams and Rosemary Carroll for their efforts going on there. And that continued on for about 4 years until about 2019. Well, in 2019, Andrew and I were kind of talking and we thought, you know, we should really try and make this a more consistent program and try a little bit of expansion. So we moved forward with getting our usual flights in the Conejos. We couldn't afford the Upper Rio Grande. Again, you can only have as much fun as you can afford. But we wanted to give this data to another group, a group who hasn't had it before, to see if it would be useful to them as well. So we started partnering with the Dolores Water Conservancy District and the Southwestern Water Conservancy District. And we got them a couple flights for the winter of 2020 season. That was that was a success. However, 2020 brought COVID, and with that brought significant budget uncertainties. So when I said that CWCB is a stakeholder-driven agency, a lot of the things that get prioritized funding come from the things that our stakeholders really want to see happen. You know, all of our grants, all of our loans, for the most part, they come from local stakeholders, and it's not a staff member coming down and saying, hey, we think you should do this. Like, that's very rare. So when we were talking about applying funding for this ASO group, we were straight up told not to. And it was because we didn't have a widespread local match, and we didn't have the federal match. So we're like, oh, okay, I guess we're not going to have funding for 2021. Well, then comes to the Rescue Denver Water and Northern with the WSRF application for this statewide ASO implementation study. We're like, see, people are interested. They want to do this, but we didn't have the state funding. Thankfully, this group was able to go forward with this water plan grant and break 2 records. First of all, they got the most money ever for a Colorado water plan grant. Second of all, the most letters of support for any water plan grant. So all of a sudden, our board and our leadership at the agency is seeing, okay, this is something that the stakeholders want, and we are a stakeholder-driven agency. We need to figure out how to support this. So this year, I'm really excited. In fact, tomorrow, we'll be going before our board for the first ever increase in funding for this program. We've been stuck at $350,000 to $250,000 a year for 4 or 5 years. And then that 1 year where we just straight up weren't allowed to get funding. And now we actually have the ammunition to go forward and ask for this increase. Now, it is a drop in the bucket compared to what a full program build out would be, but it is a small step and a small win moving forward. So we are incredibly excited to get to continue to work with these folks and get to continue to work with our leadership and figure out ways that we can continue to boost this funding and find more sustainable ways to fund it. Like Taylor said, just relying on local stakeholders is not going to get the job done, and just relying on state funding is not going to get the job done, nor is just relying on feds. It's got to be a combination of everything. And so Andrew and I, this year, we get the opportunity to take a look at what an actual state-run program would look like. And believe me, Dave Rosardo, we're going to continue to steal from you. We absolutely stole the flight coordination committee from you guys, and that idea was brilliant. It worked awesome last year. So we're going to be looking to you guys and try and steal as many ideas as we can, because we don't want to reinvent the wheel. We want to make sure that this is as good of a program as we can make it. And to add on to that, what's really exciting, so in 2015, we had Colorado's water plan come up, and it just had this one objective of filling in data gaps. It never specified ASO. It never specified any of this stuff, right? Now in 2023, with all of this stakeholder interest, with the water plan grant, with the chasm group, it is its own action now. It's action 1.8 for the 2023 Colorado water plan update to fill these data gaps, and ASO data and the chasm group are specifically called out. So this is, like Tom said, an incredibly exciting time to be a part of this. And I really just wanted to give you all that history and context of the Colorado program and some of these presentations coming up in the context of the chasm program as well.
Awesome. Thank you, guys. It really is an exciting time in Colorado. We're seeing a lot of growth and stakeholder pull. And it's thanks in a large part to the efforts of the group that Taylor and Erik are leading. And that's been great. I'll direct some attention to a few comments in the chat window there. Chad and Wes have chimed in a bit on the cost of ASO relative to value. That's certainly something that comes up a lot in our stakeholder discussions. And one of the challenges, of course, being that a large part of the value of ASO is wrapped up in avoided cost. And that is the cost of not having a flood, or the cost of not curtailing your junior water users, et cetera. And that's a bit more difficult to quantify and certainly conceptualize. But that awareness is seeping in. And and we're actually engaging with some water economists as well to start building out some of those, or quantifying some of those the benefits of improved snowpack knowledge. Let's see, we are running quite a good bit behind here, but I do want to make sure that we get any questions asked that are out there. I don't see any hands up currently. Looking pretty good. Tell you what, let's move on in the program, and then we've got a few more Colorado talks coming up in the next session, and then of course the discussion session this afternoon, where I think we can address some of these items as well. All right. Thanks everyone for sticking with us. Great stuff this morning. We'll roll into our second set of morning talks here. 3 more perspectives from Colorado, and we'll start with DK, Dave Kanzer from the Colorado River District, a longtime friend of the program, and the Colorado River District represents a pretty large swath of the western slope of Colorado. So always keen to not only have them as a partner, but to incorporate their perspectives and deep knowledge in developing the ASO program here. So appreciate Dave coming to chat with us this morning.
Great, thank you. Good afternoon. So happy to be here and talk about this stuff. I'll try to make up some time and see if this is all going to work. Got some words to share about the importance of snow, which I'm sure you're all very tuned into. For us in the Colorado River Basin, the overwhelming majority supply is from snow. It's our white reservoir, and it affects our ability to use the Colorado River and our compact entitlement within Colorado and across the entire basin. It supports our recreation, but it is under siege with climate change, because climate change is snow change. And so there's a lot going on. This is titled ASO in the River District, Colorado River District, which is a planning and policy entity in Western Colorado with a large focus and vision across the entire basin, but really focused on Western Colorado and the state as a whole. And so our objective is to develop and improve our data set, a representative data set that can help us in decision making, of course, informed decision making. And we're doing this through intensive monitoring and assessment. We are one of the largest cooperators with the USGS and their National Water Information Network. Dust on snow is a big issue. I see Jeff Derry from the Center for Snow was on, and then ASO. So we need to connect that research and monitoring with operations to help us with forecasting, to perform decision support and support all of our decision-making frameworks. So doing that really helps us sort of mitigate and adapt to our changing environment. We know that stationarity is dead. We are no longer able to rely on historical information to make good decisions. And in fact, new technology or old technology, which is being reformulated, like cloud seeding, irrigation optimization, and reoperating reservoirs, is all keyed into good information, and ASO is a big part of that, we think, in the future. And we're kind of ASO rookies when it comes down to it, because we don't have a lot of history with that program in Western Colorado or across the Colorado River Basin, but we sure are interested in doing so. And for those that are not knowledgeable about the Colorado River Basin, it's an interesting system. It's kind of overused, over allocated. The only major river covers 7 states within the natural basin shown in black, and a lot of outside areas that export a significant amount of water to areas like the Front Range of Colorado, all the way down to the coastal plain, Southern California. So water and snow, critically important to 2 countries and 30 tribes across this region. Now, the upper basin is a story of supply where approximately 90% of the water arises in small areas, and I'll show you those in the high watershed. And the lower basin dominated by 90% of the folks, and all that demand for Colorado River water makes it a really challenging system to operate. So when it comes down to it, where's the water? And this may be obvious to many of you, but when you show this plot to some folks, it's an eye opener that a very small fraction of the Colorado River Basin is in that water yielding, snow yielding area. And so the blue areas where your average annual precip is, significant, is extremely small. And so that's why ASO is so important for us to understand where the snow is, when it is deposited. And so this plot drives down into that. And this psychedelic kind of color scheme shows you that of those areas where precipitation is high, only a very small fraction is above or in the sweet spot, I would call it, from say 9,000 feet above mean sea level to about 10,500, 11,000 feet, where again, we want that snow to fall and to be preserved, and that when melt comes, it helps us feed our systems, our river systems. This chart here really drives home that point. And, it's startling when you think about the entire area of the Colorado River Basin, how little of it is in that sweet spot. 10 to 12% in aerial extent is where that snow falls and again is preserved, and that we really need to understand that distribution and the temporal characteristics of it that ASO can really help us with. And if you drive down even further, drill down into the Colorado River District itself, which is 15 counties in western Colorado, this is where the majority of water that flows into Lake Powell arises. Almost 65 to 75% in this small area flows through, arises in, and ends up flowing into Lake Powell. So again, critically important for us to understand this resource for the 40 million people that rely upon it. And so right now, unfortunately, we know that the bullseye of climate change is right on top of us, right in our small polygon. That most important part of the Colorado River Basin is being impacted with temperature changes approaching almost 5.5 degrees Fahrenheit since 1895. And of course, there's other areas within the Colorado River Basin or served areas outside, inside, that are also under siege with this climate change. And if you look at that in even more detail for us and our 15 counties in western Colorado, you can see it's not as dramatic in the headwaters, but we are seeing significant change, which means more rain, less snow, and a shorter, sharper snow accumulation season. And so for the geeks in the crowd, this is the plot that really tells the whole tale. And I stole this from Deems, so thank you, Jeff, for this. I augmented it a little bit, but it shows how we get the information in the snowpack over time from November to May, when the snow accumulates in the high country. It's a story of accumulation and ablation. We've heard this in the last 2 days. We know that SWE is not only an important parameter of depth, but also density. Within that, you have layering, you have dust, you have wide distribution spatially, temporally, and runoff, and the dynamics associated with runoff is affected by soil moisture and soil characteristics. And it's a tough thing to measure because of these things, where point measurements and indices that we have relied upon over the past really are not sufficient to capture this diversity. And so I added to this plot these sort of decision-making lines, or when we as water managers are trying to figure out how to make decisions. And you can see kind of as the snowpack grows throughout the year, we actually have to make decisions before the annual seasonal peak. In January, we're trying to make releases from the reservoir for to avoid anchor ice or environmental impacts where you can have benthic organisms being suffocated by anchor ice, which affixes to the stream bottom if there's not enough flow in the river. So we may be proactively releasing water at that time, not knowing what our water supply, our annual water supply is. In March, we're trying to make plans to fill the reservoir. That's another critical time because in a lot of our facilities, we are competing with other users, which are either exporting water out of basin. You heard about the Roaring Fork Basin where Rudai Reservoir is located. It's about 100,000 acre foot facility. It is actually split between East Slope and West Slope beneficiaries. And decision points again are made on how to share that resource before you have the full picture. And this is where ASO can come in and provide information, hopefully in real time, to at least give us a better picture of what is out there, and then through modeling efforts, what is to come. And then in the summertime, after snow accumulation has finalized, we're figuring out how to make releases for endangered fish downstream. And it's probably an issue that many reservoir folks, water resource specialists on the call are very familiar with. And again, for the geeks in the crowd here, you can kind of see how snow depth changes and snow density can change throughout the season, which complicates these decisions, and our strategies relied on those decisions or informed by. So, it's really a quick tour around the Colorado River District and around the basin. We know the problems. We know the needs are basically for better forecast reliability. And that's informed by things like ASO. We need more snow. We get that through augmentation of cloud seeding. And then we need to integrate that with the rest of the data that we are collecting. Again, whether it's soil moisture, whether it's hydroclimate information and signals from ENSO, et cetera. So again, hopefully catching up on time. Happy to take questions. We have a really good website and a lot of social media here for folks that don't know about Colorado River District. So please look us up and reach out to me if you have any follow-ups. Thank you so much.
Awesome. Thanks, DK. It never ceases to scare me a little bit seeing those temperature change plots for the well, the whole CONUS really, but right on the district, it's pretty impressive. Let's see, I don't see any hands up currently. I do know our next speaker, Craig's got a bit of a time constraint, so maybe we'll just move right on and hear from Craig, and then we can keep an eye on the Q&A. Folks, if you got questions for DK, please type them in there. We can move forward. Thanks a ton. Next up, excited to hear from Craig Cotten, who's the division engineer from Division 3 in Colorado, which is the Rio Grande Conejos basins down in south central Colorado. And as Taylor and Erik laid out earlier, we've been working with Craig and folks down in that district for a good bit of time, since 2015, I think. Anyways, really appreciate you being here today, Craig, and please take it away.
All right, thanks, Jeff. Yeah, I appreciate you giving me some time to talk about the Conejos Basin and what we're doing down here. And as Jeff said, as some of the other presenters have said, we've been dealing with stream flow prediction ups and downs and difficulties for a lot of years, and we really appreciate ASO and Chasm coming in and helping us out with this. Today, I'm going to talk specifically about the importance of stream flow prediction and accuracy of stream flow prediction for the Conejos Basin in Colorado. And the Conejos Basin is actually a very small basin in the state of Colorado. And this is what we call our snake diagram. This is just a diagram of the river flows that flow out of Colorado and into other states. And so in the bottom part of the state of Colorado, in this picture, you can see the Rio Grande and a little tiny snake there on the Conejos coming into the Rio Grande. And that's the Conejos River is the biggest tributary to the Rio Grande in Colorado. And so we have the same needs for accurate stream flow prediction that I think most everybody has. Our farmers and ranchers need to know how much water they can expect so that they know what to plant for the coming year. Our municipalities need to know how much water they're going to expect so that they can kind of plan for the future as well. But we have maybe even a little bit more need for accurate stream flow prediction, and that's because we are part of a bigger system, not just in Colorado, but also in New Mexico and Texas. And that's the Rio Grande starts in Colorado, but it flows through New Mexico and into Texas. And it's actually even used by the Republic of Mexico. So the water that we have up here definitely has an impact on a lot of other people downstream and the amount of water that we send downstream. So we need to know how much water we have up here so we know how much water to send down to those downstream states. I think most every place in Colorado on the big rivers has a compact. We've got the Colorado River Compact, the Arkansas South Platte compacts. So a lot of compacts that Colorado deals with, but the Rio Grande Compact is a little bit unique in the way that Colorado is tasked and required to deliver water to the downstream states. So this is a graph of that obligation that we have. And so actually Colorado has two obligations on the Rio Grande Compact. One is on the Rio Grande main stem, and that's that darker line on this graph. And then the other one is specifically for the Conejos River, because the Conejos is actually operated as a separate part of the Rio Grande Compact. And so we have separate delivery obligations. And unlike some other compacts that Colorado has, the amount of water that we owe to the downstream states changes on a yearly basis. And it changes based upon how much water we have up here in Colorado. And that's considered our index flow. And we have index flow gauges on both the Rio Grande and the Conejos systems that determine how much water we have up here. And from that, we can determine how much percentage-wise of that water we need to deliver down to the downstream states. And so you can see on this graph that the Conejos River, that pink line there, is fairly volatile. If we have a really low water year, we don't owe anything at all to the downstream states. That's very rare when that happens, and it's not a good situation when that happens, because that's saying that we don't have much water up here in Colorado either. But then on the other end, if we have a high year, we could owe as much as 70% of that water down to the downstream states. And so it's a like I said, a very volatile way to look at it, and a very volatile way to have an obligation under a compact. And so we need to have good stream flow predictions, and I'll get into that here in a minute. So this is another way to just look at the obligation that we have on the compact. And this green area is the amount of water that we owe to the downstream states. And then that white area that says available for depletion, that's the amount of water that Colorado can actually use, and our water users can actually use and deplete from the Rio Grande in any given year. And so you can see at the bottom end of that, when we have very low flows, like I said, we owe very little to the downstream states. But when we have high flows, we can owe nearly 2/3 of that water that we have in the system down to the downstream states. And it's kind of an interesting graphic. You'll notice at about 400,000 acre feet that Colorado can't use any more of the water, even if we get twice as much water as that. We can't use that water. We have to pass all of the excess water down to the downstream states. So that's an important consideration too, and something that we deal with on a daily basis. This is a histogram of the Conneaus River system. And this is the upper index station, Conneaus River near Bogoti. We actually have 3 index stations on the Conneaus system, one on the Conneaus River and then 2 on big tributaries of the Conneaus. And you can see that we can have a situation like we had in 1920 of almost 450,000 acre feet of water in the system. And as opposed to that, in 2002, we had just over 50,000 acre feet. So a very wide range of flows that we can have on the Conneaus system. And even more recently, you can notice that 2018 was about 130,000 acre feet. 2019 was over twice that amount at almost 300,000 acre feet. And then 2020 was back down at about 140,000 acre feet. So wide range and fairly volatile amounts of stream flow that we can have on the system year to year. So I'll go back to this graph and just give you an idea of what we have to look at and why stream flow prediction is so critical to us. So under the Conneaus system, on an average year, we have about 300,000 acre feet of total index flow. And of that, we go use these graphs and go across, and we owe about 36% of that down to the downstream states. So it's about 109,000 acre feet. And so that's kind of an average year. If we have a little bit less than average year, say 100,000 less than that, we owe only 22% at 45,000 acre feet. So a big difference, just dropping 100,000 acre feet, we owe much less. On the other end of the scale, if we get another 100,000 and go up to 400,000 acre feet, we owe 188,000, or about 47% of the total supply that we have up here. And so that's the volatility that I was talking about there, is that can really change a great amount based upon how much we have up here. So for instance, the difference between 300 and 400,000 is 100,000 acre feet, and we actually owe 79,000 more of that total, 79% of that, to the downstream states. So this is where the stream flow forecast gets really critical for us. Because that annual index flow is a calendar year flow, we need to know what that index flow is going to be at the beginning of the irrigation season. So April 1st, or ideally maybe even in the middle of March, we need to have a very accurate stream flow prediction to know whether it's going to be, say, 300,000 or 400,000. And then we start basing our year upon that. And we actually curtail ditches. We shut down ditches on a daily basis to get that water down to the downstream states. This is another critical part of the Conneaus system and the Rio Grande as a whole, is that we don't have large reservoirs that we can store that water and later release it if we need to, or keep it in storage if we've delivered enough water to the downstream states. So we just don't have that ability. So we have to rely on that stream flow prediction and determine how much we're going to deliver on a daily basis. And we do that on a percentage wise. And so that's kind of how we use the stream flow prediction and the models that we get, and why it is so critical. Another thing that I wanted to just point out is the water rights on the Rio Grande and the canal systems. And so this graphic shows that the red line here is the water rights on the canal system, and the blue is the Rio Grande. So we actually started having water rights adjudicated and appropriated on the canal system in 1855. And by about 1900, we pretty much had the entire flow of the canal system appropriated, and all of that water could go into ditches that were in existence at that time. There were a few ditches after that time that were put in, but by and large, by 1900, all the ditches were put in. And so if we have to curtail any ditches to get downstream water rights, downstream states, their water, we are actually curtailing pre-1900 water rights in almost all cases to get that water down there. So very critical that we make the right decision on that too. And this is actually a graphical representation on the Rio Grande, but it gives you the same ideas on the canals. So these lines represent different ditches in the system, and the black line is the average flow for each day throughout the season. And so if you're a ditch that's at the bottom there, a senior ditch, you get your water pretty much regardless of what happens in the system. But as we go up, you'll only get your water for maybe a short period of time, and that's based on when we have that higher flow. And that box at the very top represents ditches that are actually in existence and have a water right, but in a normal year they wouldn't even get their water. And so they're again very critical that we make the right decision, and that we don't over deliver water down to the downstream states and actually cut our water users out of water. But similarly, it's good that we don't under deliver, because if we under deliver, we have to make that water up in the next year's time period, and that could actually hurt somebody that otherwise would have gotten water that year too. So this is just a graph of kind of how we do that. So we do actually curtail percentage-wise, like I said, on a daily basis throughout the irrigation season. And here again, this is the Rio Grande, but it's the same for the Caneo system. And this is just using 2011 as an example. And that would be the red line there, and each of the daily flows. But the green line represents the amount that was actually available for our water users in any given day. And so you'll notice that we actually did take the total flow and cut it down by a certain percentage. And that what was left over is what we can use for our farmers and ranchers and our irrigation demands up here in Colorado. The remainder has to go down to the downstream states for their use. And finally, I did want to just give you an idea of what we're actually doing this year. And so this is actually what we're ending up with for this year. And this is the curtailment of ditches on the canal system. And so the wintertime, the January 1st through March 31st, is considered our non-irrigation season. And so at that point in time, we're delivering 100% down to the downstream states, because the ditches don't need it up here. But starting April 1st, we do go into a situation where people are irrigating and they want that water, but we have to cut back on by a certain percentage. And so this year, actually, we started with a 20% curtailment, and got some newer forecasts starting around the first part of May, and those forecasts actually went down. And so we dropped our curtailment down to 16%. Then new forecasts at the first part of June, and we actually dropped that curtailment down to 7% at that point in time. And kind of a very unusual situation, but as you all know, then starting in July, we started to get rain, and we decided that we actually did need to deliver more because we were going to have a higher obligation on the Conneaus and on the Rio Grande under the compact. So we went up to 15%, and then in the first part of August, 26%, and then by the middle to late part of August, we realized that we were way behind on our deliveries down to the downstream states. And so we actually started delivering 50% of our flow down to the downstream states. And now we're actually experiencing a dry period, and our rivers are drying up. And so we're starting to go down on that percentage here too. And we can do that, and it's not a really big deal as far as just mathematically and doing the calculations to get those percentages. But what that really does to our farmers and ranchers, they're expecting perhaps to stay at 20%, 15 to 20% for the entire year. And then we get into mid-August and September when they really need that water. And now all of a sudden we're at 50% curtailment. So we're sending 50% of that water past their head gate down to the downstream states. And that's a tough pill to swallow sometimes for our water users. And so we really try not to do that. And that's really the reason that we have these great needs for accurate stream flow predictions on the Kanneaus system. So I think that was my whole slide there. And if there are any questions.
Awesome. Thank you, Craig. I'm always struck by how in most basins you get more water and there's more water available for everyone, but you've got the opposite problem, which certainly is at least a wrinkle, if not a completely different scenario. Any questions out there for Craig or for DK?
Don't see any hands.
Joe's got a hand up or a finger.
Just a real quick one. For your downstream obligations, is it strictly water year? I mean, or are there requirements of when you downstream contribute?
That's a good question. It's a calendar year basis, and there are no restrictions. So, for instance, if we had a very large reservoir at the state line, we could deliver it all December 31st. But but we just don't have that ability, so we have to do it on a daily basis.
It's so cool seeing the complications. I mean, I'm sorry for you, but it's so cool seeing all the details on each of these basins. Thank you very much.
We just had a question popped into the chat from Josh Sturdivant. How has the relatively recent introduction of WGRFC water supply forecasts in the Conneaus changed operations?
Yeah, so because we rely so heavily on stream flow predictions, we actually use 3 different stream flow prediction models: the NRCS and the Weather Service, and then the Wharf Hydro models is something relatively new, and ASO in cooperation with the Wharf Hydro models. And that's actually really improved, I think, the modeling accuracy. But as we all know, there's some years where it's just not quite as accurate. And so having 3 different models that kind of look at things in a little bit different way, I think really has helped us. We do compare those and contrast those to each other each year, and try to use all 3 of those models to come up with a good scenario.
Awesome. Let's see, we got a question from Gus in the Q&A asking how much can ASO data collection help, considering it seems like anomalous precip after forecast data is the primary issue with the monsoon this year.
Right, Gus. That's definitely true this year. The stream flow forecasts, you know, we couldn't use those to determine that we were going to have a really wet late summer season, and so that's definitely something that we just kind of struggle with. Ideally, it'd be great if we could come up with a model that would take that into account, those monsoon seasons, but we just don't have something that's really accurate, at least at this time.
But with respect to
piling on top of a poor snowfall knowledge in addition. Sorry, Tom, I stepped on you there.
I was just going to say, with respect to snowfall, though, that's where the build out of programs can help. Obviously, we're not a airborne rain observatory. We can go make the snowpack measurements after a snowfall event, and that's been one of the questions, and that's the main response is the utility. Likewise, during the snowmelt season, is that you do get snowfall events, and you can go capture those and update the model accordingly.
Yeah, and that's when we get the most of our runoff is because of snow, and so that's definitely the by far the biggest part of this. And if we can get accurate stream flow predictions of the runoff season because of the snow, we can deal with the monsoon seasons.
Great. Awesome. Thanks again, Craig, for jumping in. I know you got a tight schedule today, and apologies for running behind here. But great to have you in the mix here. We'll move on to our last talk before lunch. Nathan Elder, who's the raw water supply manager for Denver Water, and has been a partner with the ASO program for a number of years now. And Nathan, good to see you.
You too. Thanks, Jeff. Let's see. Let's get this up. All right. Yeah, thanks for having me. I manage the raw water supply section for Denver Water, and we've been using ASO data since 2019 above our Dillon Reservoir in the Blue River watershed. And today I'm going to talk about a little bit how we use this data. I think, you know, for the past few years, we've proven it helps reservoir operations, and how we're starting to branch that out and helping inform the local community and local businesses and a lot of stakeholders that are in this area. So a little bit of background on Denver Water. We've got a roughly 4,000 square mile collection system. Our Dillon collection system, or Blue River collection system, is outlined in blue. Our South Platte, that is in yellow. And then our Moffett and Williams Fork collection system are in green and outlined in pink. Roughly half of our water supply comes from the West Slope, and the other half comes from native supplies in the South Platte River. Focusing in a little bit more on Dillon Reservoir and that Roberts Tunnel collection system. So Dillon's our largest reservoir. It's 257,000 acre feet. That's about 38% of Denver Water's total storage. So really important reservoir for us. Connected to that reservoir is the 23-mile long Roberts Tunnel. And this is a trans-basin diversion that brings water from the west slope over to the east slope. And you can see here in black is the Continental Divide. And within this watershed, we've got several ski areas. We've got 4 snowtels, and it's become a really popular recreation area. Again, you can see here the map of Dillon Reservoir. Downstream, you've got Silverthorne, you got the town of Frisco,
Dillon, Breckenridge is upstream. And it's really, the reservoir is a big recreation amenity for the communities up here. And it's a really important part of their community. And we try to manage it to maximize what we can for them. And there's a lot of competing interests here. You've got water supply. You know, the biggest driver of Dillon Reservoir is to maximize water supply and fill that reservoir. You got 2 marinas on the reservoir, rafting and fishing below the reservoir, and then flood control with Silverthorne, again, below downstream of Dillon. So our 2022, we had 2 surveys, April 19th and May 26th. What these surveys really did for us this year is, you know, they confirmed that CBRFC most probable forecast. Looking at that forecast, we knew it was going to be a below average water supply year. Again, average April through July inflow to Dillon Reservoir is about 163,000 acre feet. So you can see here in the April flight, about 150,000 acre feet of water above the reservoir, and we know some of that's going to be lost to soil moisture and evap and other things. And we had a big hole to fill in Dillon of about 45,000 acre feet. You can see between April 19th and May 26th, between those 2 flights, within the snowpack, we lost about 58,000 acre feet. During that same time, April 19th to May 26th, we saw about 32,000 acre feet of inflow into Dillon. We knew this was going to be a bad year for soil and moisture. Again, CBRFC had been telling us that, and something that we should watch out for. And then also from these forecasts and just computing inflow outflow, we knew our outflow from Dillon Reservoir for the duration of the summer was going to be at our minimum flow near 55 CFS. Average is closer to 700-800 for that summertime peak period. So at Dillon, you know, especially with the pandemic in the last few years, you know, we've really seen increased recreation both on the reservoir and below the reservoir. We've got a lot of different stakeholder groups, fly fishing community, you know, downstream of Dillon on the Blue River. There are stretches that are still designated as gold medal waters. You've got rafting that occurs not every year, but pretty frequently. You've got, again, 2 marinas on the reservoir, a lot of on-water recreation. Stand-up paddleboarding has been a new popular recreation at the site as well. And we really want to try to give these, provide stakeholders with the best forecast that we can based on our reservoir operations and based on the data that we have, so that they can make the most of the water available to their specific purpose. So looking at this year, early on when we had our ASO flights, and again, we knew reservoir outflow was going to be 55 CFS pretty much all summer. So the desired range for rafting is closer to 500 to 1400 CFS. So early on, we were able to let the rafting companies know, unfortunately, there's not going to be a rafting season on the Blue this year. And, you know, we understand that's frustrating for them, but having the ASO data and having this information and the certainty, we can tell them that with certainty, and then it allows them to move their operations elsewhere to other rivers, not book those trips that they might book, hoping that the flows might happen and then have to cancel those later and end up with frustrated customers. So it's, you know, they may not like the answer, but it does help them in a lot of different ways. You know, the same thing with fishing this year. So again, it's those gold medal waters that tends to attract a lot of out of state and fly fishermen and trips booked from those out of state participants. And we were, again, able to provide them the forecast that, you know, unfortunately this year, the Blue River below Dillon's only going to be 55 CFS. It'll be outside of your desired range for fishing, and it helps those guiding services move to other locations that can provide their clients a better service and have, you know, that data and information long ahead to be able to move those trips and reschedule those trips. You know, for flood control this year, again, the same thing. Our action level is 1800 CFS. We knew we were only going to be releasing 55 CFS, and we were able to communicate that to the local community, local first responders, so they knew this was something they wouldn't have to worry about this year. And then further below the reservoir on I-70, the Colorado Department of Transportation, they're doing a major project on that bridge, and they're able to do a lot of work in that river corridor this year and move around some of their work plan, knowing that throughout the whole summer, they were, again, only going to see 55 CFS, and they had a lot of area to work and didn't have to worry about flooding or moving their work sites. They were able to get a lot done. Again, for Denver Water, looking at hydropower, we've got a hydropower unit at Dillon Reservoir. The maximum outflow from that maximum generation flow is about 100 CFS. You know, looking at, again, we're only going to be releasing 55 CFS all year, so we needed to look at other places within our system that we could change our operations to potentially generate more hydropower. And then lastly, you know, looking at the marinas, there's 2 marinas on Dillon Reservoir. Each month we provide them with updated forecasts, and to try and plan their yearly operations. So in this chart, we've got our forecast here, our average forecast in black. The range of that forecast is outlined in blue. The gray line at the top is full reservoir elevation. These 2 red lines are elevation 9012, where the marinas are fully operational, and elevation 9004, where the marinas are not operational. So you can see something went wrong here with our forecast. Keep in mind, Dillon has the Roberts Tunnel attached to it, and in our South Platte system, we don't have ASO data. And our forecast there that we were using was about 20% off. So when we were looking at this originally, we didn't think we were going to be bringing over as much Roberts Tunnel water and drawing Dillon down as much as we did, as shown in the orange line. And I think, you know, if we're working on it with some partners, and hopefully we can get ASO in that South Platte data next year, because I think that would, again, help us with these forecasts and able to help those marinas know what to expect for the coming year. So just to wrap up, we know ASO data can improve our forecasts and improve reservoir operations, but you know, we're looking at what else can these forecasts do in terms of informing recreational, construction, energy production, all kinds of stakeholders that we have within our collection system. And, we have seen that these more accurate forecasts help us build trust with those stakeholders. Every year in May, we go over to the West Slope and we let them know what we expect to happen at Dillon Reservoir, and the better forecast we can provide them, the more trust we're able to build. It's a lot better to let them know bad news with confidence than give a lot of uncertainty and have them have to deal and plan with their uncertainty. And helps them improve their business operations, and again, just improving those stakeholder relations and communications. Again, thank you for having me today, and I'll take any questions now that you might have.
Awesome, thanks, Nathan. Definitely struck by the kind of system interaction with the South Platte there as well. It's and you didn't even mention all of the down the Colorado direction, all the obligations that you guys have to Green Mountain and all of that. And so
and just to be fair to yourself, you ought to have another line on that plot showing actual plus the extra to the Roberts Tunnel.
Yeah, it's true. Any questions out there? People eating lunch already, maybe? Nathan, can you speak to, you mentioned the stakeholder confidence. How does increased confidence in just, with one part of your system propagate into the rest of it? So you mentioned the diversity of different sources you guys have. There's Dillon and the South Platte, which are linked directly by the Roberts Tunnel, and then the Moffett system, which goes into South Boulder Creek and is a separate system entirely, at least on the diversion end of things. How does increasing operational confidence in one part of your system affect management of the other components, even if you don't have as good of or as comprehensive data sets there?
Well, yeah, I mean, all of our system is really tied together, and we use this forecast to look at everything there. Right now we're currently have one of our reservoirs, Gross Reservoir, on our north system. It's under construction, and we have a storage restriction on that reservoir, and then that reservoir is connected to a treatment plant. So we know that treatment plant can't treat the same volume this year that it typically does. And then we know we have to use more of the south system, so that South Platte and Dillon Reservoir supplies. So having more accurate forecast there gives us an indication of how low or high we can actually stress that north system. And then how much that, if we're maxing out our north system, then how much of an impact is that going to have at Dillon Reservoir and downstream on the Blue, downstream on Green Mountain, and yeah, how much are we going to then owe in a substitution?
Complicated. I think a great example of kind of challenging hydrology and human hydrology and challenging stakeholder base as well. Anyone else out there? Start asking quiz questions. Make sure people are paying attention. Oh, there's Matt Meadows. Okay, go for it, Matt.
Yeah, I was gonna say I like this order of talks between Nathan's clear understanding of all the different stakeholders, and then just letting them know good news or bad news, and then Cotten's talk about how different canals are going to be running depending on how the hydrograph goes. And we have a great example in the Kings where the high-speed rail has decided to cross the river in a spot where it's 3 different channels instead of 1. And they always call and ask, is there going to be water there? So, with ASO data and the forecast, we can confidently say, maybe. But knowing where water is going to be flowing within our service area, dependent on how we have to divide up the water based on all of these different agreements, is important and can inform that type of construction, which is pretty major construction if you ever want to look at it on Google Earth.
So a certain maybe is better than an uncertain no.
Yeah, I mean, if you tell them no, then we're actually going to get rain.
Which is better.
Yes.
Yeah.
Yeah, exactly.
I think Murphy was a meteorologist.
That's right.
Awesome. Anything else? I think it's lunchtime, actually. Nathan, thank you so much. Been great to work with you over the years, and looking forward to next season as well. And thanks for laying out some of the challenges you guys face there.
No problem. Thanks, Jeff.
All right. I'll let Kate take us into lunch, and then we'll come back afterwards for a few science talks from some of our DRI colleagues.
So now we're recording again, but thank you so much, Adrian.
Yeah, no problem.
Any other questions out there? Or comments? We'll allow comments too. I have kind of a conceptual question, Adrian, that what's your sense, you guys are testing a bunch of different kind of forest metrics, and the array of those out there is, well, it's almost limitless. Many of them derived, from fairly coarse empirical methods that we're trying to use remote sensing to sort of replicate, and others that really, on the other end of the spectrum, take advantage of super high resolution, LiDAR point clouds or other data sources. What's your sense, in this sort of scale aware context that you guys are operating in? What's your sense on kind of the sweet spot for the type or even the individual forest canopy metrics that seem to respond best to snowpack dynamics?
Yeah, that's a great question. There's the approach of throwing everything into the hopper and seeing what works. I'm very much more of the process-oriented type person, and I think it actually worked well in this study where we saw a sort of simpler approach, which is just effectively how much canopy is there that's taller than 2 meters, which you can get pretty close to with Landsat and things like that. And then something about the size of the gap. I think what we're converging on is some combination of those two things, maybe with something around edges and how edges interact with radiation and prevailing winds. But it's hard to put these things back together in a way that's really simple. But I do think the fine scale forest structure matters, which really means that LiDAR has a lot of value.
Cool, and that that kind of thing dovetails with what Liz was getting at a moment ago as well. As you change ecosystems and forest structure, maybe the appropriate indices change as well. But really cool stuff. So stoked to see how it's progressing. Oh, Pat's got a question.
I was just building on what you were asking, Jeff. There's plenty of historical photos prior to fire suppression going on. Not a lot of data about what we're talking about, but certainly some pretty good hydrological background in that for the last 125 years. I got the impression that forest thinning was trying to recreate that, quote, natural setting prior to influence of Europeans. And I was curious just to build on that idea with what Jeff is saying, that Does that make sense, or is there some other best case that you expect to come out of that?
Yeah, I mean, I'm not a forest ecologist, and I could get myself in a lot of trouble, like sort of speaking for all the benefits that can come out of this. I guess what I would say is that the focus has really been about restoring that kind of restoration, mostly around fire, right? As it being a more fire safe. And there's restoration that's restoration focused, right? And then there's sort of thinning things that are more emergency focused, which is, again, really just about reducing fuels. There's been a lot of research around wildlife in those kind of settings, large seral gaps and the value of small clumps and big gaps. And but I think the influence on hydrology is sort of less clear. And in some ways, maybe it's obvious. Maybe it's obvious that we should see benefits in a more open, taller trees. But it really helps the Forest Service to be able to say this has mutual benefits and really point to that. I'll also say we don't have 100-year, 300-year trees all over the landscape, right? So we can try to recreate that landscape, but given disturbance and the future climate, we're never really going to be there, in my opinion.
Fair enough.
Awesome. There's a couple more questions coming in, but I
see them.
think I'd like to move on just to stay on time, and then I'm seeing some discussion potential for the discussion session this afternoon. Are you going to be around for that, Adrian? Can you?
Yes, I can stick around for that.
Fantastic. All right. Thank you, Adrian. And our next speaker, as Adrian mentioned, is working with Adrian, Eli Boardman, who coincidentally has the same surname as one of our co-founders. Eli Boardman. And Eli, you're looking pretty chipper for somebody who just completed a pretty massive transect of all the 13ers in Wyoming in a very short amount of time. Congrats on that. Anyways, Eli will be talking about wind redistribution of snow as a driver of summer stream flow and agricultural resilience.
Thanks, Jeff. Let me just share my screen here. Okay, I think that's sharing. Thanks so much for the opportunity to talk. I'm Eli Boardman. I'm a second-year PhD student working with Adrian Harpold here at UNR. Today, I'll be presenting on some of my recent research using the first year of ASO data in Wyoming. Just super exciting to see some of this data. And specifically, I'll be looking at the wind redistribution of snow as a driver of summer stream flow and agricultural resilience in the Wind River Range, which actually, as Jeff mentioned, I just spent a week backpacking through, so that's why my voice is a bit hoarse. Sorry about that. Before I get started here, I'd just like to thank some of my amazing collaborators, especially Adrian at UNR, as well as the Wind River Water Resources Conservation Board, which represents the tribal water rights interests of the Eastern Shoshone and Northern Arapaho tribes. They've been really key partners in this and worked really intimately on making this project possible and making it as relevant as possible for the water rights of these tribes. I'd also like to thank the Wyoming Department of Game and Fish for letting me install a stream gauge, all of ASO, and National Science Foundation for funding. So the Wind River Range is in west central Wyoming. I've got it circled over there on the map. If anyone really likes backpacking, I highly recommend going there. It's a beautiful area, has the highest peak in Wyoming, as well as the largest glaciers in the US Rockies and the largest glaciers in the US, in the lower 48 outside of Washington. And these high snowy mountains provide a really key water tower for the arid valleys on either side, both the Wind River Valley and then the Green River Valley, which feeds the Colorado. There's also a really big focus on tribal water rights in this area, as much of the Wind River Range is in the Wind River Indian Reservation and provides water for indigenous communities and tribal agriculture programs. So this is an overview of the basins I'm studying. It's 8 adjacent east side basins. So they're all east of the Continental Divide for now. so the other side from the Green River. But these all drain into the Wind River, and you can see the overlay of the reservation boundary on that. So there's a lot of this high snowy glaciated area, which then drains down and provides that crucial water for the arid agriculture in the Wind River Valley. Now, when we compare the stream flow from these different basins, there's some really interesting observations in the annual hydrographs. Just ignoring some of those really low ones that are kind of just lower elevation basins. The thing we really notice is that of the major alpine basins, the peak magnitude and timing of stream flow is fairly similar, but in the late summer, July, August, September period, there's this large discrepancy between some basins that are producing several times more water than others based on, relative to their area. So trying to explain that difference in stream flow patterns is going to be the main focus of this project. And it's a really important difference because that late summer stream flow is really important for agriculture in the valley. So besides just the local stakeholders and all of that local microcosm, why study the Wind River Range from a scientific standpoint? Well, it's really interesting because it has a ton of complex hydrological storage processes all compacted into a nice tight geographic area where they can observe the way that these processes all interact in one place. To start, we have the ephemeral snow, just your winter snowpack, as well as these large drifted areas where the snow persists late into the summer in these huge wind drifts and even multiple years of persistent drifted snow sometimes. And then if the snow lasts long enough, it can turn into a glacier. And I promise that actually is Wyoming. That was just this past week. That's not Alaska or something. So we do have some pretty good glaciers in the Wind Rivers. They are rapidly retreating, sadly, but they're still there for now and definitely a key part of the active storage. There is a little bit of groundwater, primarily around the edges of the Wind River, so that's a small spring. And then there's some really giant lakes all throughout the Wind River high country. For this project, I'll mainly be focusing on the cryospheric storage processes, but these liquid water storage processes are something I do want to come back to with additional research in the future. So our motivation for this project is that these cryospheric storage processes are undergoing rapid change and disturbance. And that's true, across the whole world, but it's especially true in the Wind River Range, where the glaciers have been observed to be rapidly retreating and will be largely diminished within a few decades. And the snowmelt is consistently shifting earlier. So with these changes to the active storage processes, we wonder what are the implications for the water supply and the downstream users. To understand this, we really have to understand which storage processes are currently active and how they interact to explain the observed patterns in the summer stream flow in the historical record. Then if we can understand some of the current storage processes, then we can try to ask how resilient those processes might be to disturbance from climate change and what the implications of those disturbances would be for water users as these storage processes shift. So just as a starting hypothesis, when we look at that variation in the late summer stream flow between these different basins, the really obvious thing that pops out if you just look around at some of these basins in Google Earth or backpack through there for a few days is that the basins that produce a lot of late summer stream flow also happen to be the basins that have basically all of the glaciers. So kind of the obvious hypothesis is maybe that, quote unquote, extra water is coming from glacial mass wasting. And if so, that could be really a bad thing for the agriculture in the valleys, because as the glaciers retreat, you might lose that extra late summer water source. But the good news is that the existing glaciological literature on the Wind River Range just doesn't support that extra stream flow coming from the glaciers themselves. If you do the mass balance on the glaciers, they seem to only be contributing a few percent to the annual stream flow. And to fully explain that difference, you would basically have to melt the entire glacier every year. So there's just not enough water in the glaciers, and that extra stream flow must be coming from somewhere else. The other kind of obvious hypothesis is just the difference in spatial precipitation patterns. Maybe the basins that have more stream flow just get more precipitation or more summer precipitation. But normalizing the stream flow record by some gridded precipitation products doesn't really explain this variation in the late summer stream flow. On the right, you can see just the 2022 hydrograph for a few of these basins, normalized by the October to July precipitation. It matches pretty well up through about the peak flow, but then you can see in that late summer, July, August, September period, there's this big divergence where some basins are producing way more water than others. Now, of course, we might wonder if those precipitation products are not really accurate across the, these high remote mountains without any high altitude precipitation observations. And that's where ASO really starts to come in, is that we can get a good fix on the spatial distribution of the precipitation inputs using the June of 2022 ASO SWE map. That's the same sort of hydrograph on the right, where it's the 2022 runoff normalized by ASO SWE. And you can see that the basins are behaving very similarly up through about peak runoff. But then after that, there's again this divergence where some are producing considerably more late summer stream flow than you would expect just based on the kind of bulk spring SWE volume. So our final hypothesis is that the snow is persisting longer in some basins and that extra summer stream flow is coming from essentially extra summer snow. Just doing a little cursory analysis with the MODIS fractional snow cover time series, you can almost recreate the relative stream flow patterns from the relative snow covered area of these different basins. So snow persistence does seem to be a pretty promising angle on this question. Anecdotally, there's a couple of pictures from a few days apart at the same elevation, completely snow covered, completely snow free. So why does the snowpack persist longer in some of these areas and have some basins have so much more snow in the summer than others? The answer actually seems to be in the name of the places in these pictures. One is a basin and one is a flat. And the basin traps the snow and it's sheltered from the wind. And the flat, the snow all blows away. The wind river range is notoriously windy. This weather station I built just at a low elevation in the valley, consistently records 40 to 60 mile an hour winds all winter, like basically every day, which is really, that's the top end of the blowing snow transport scale. So there's just a tremendous amount of wind-blown snow in the Wind River Range in winter. And you can observe this anecdotally, going out and doing some snow pits, seeing this really low density winter snow up in the Alpine, huge winter winds, massive clouds of spindrift coming off these mountains, huge amounts of sublimation in the areas that are exposed to the wind. And then conversely, going out and doing some summer snow field work, we see these massive drift zones, really high density seasonal snow. That's not like glacier ice or neve or something. That's a single year snow of 0.6 grams per cubic centimeter. And so our hypothesis is that these giant drift zones are strongly contributing to this late summer runoff from certain basins. But that's all just kind of anecdotal. And that's nice. We saw some drifts, we saw some wind, but how do we map or observe these drift patterns across the whole landscape? Well, of course, that's where ASO comes in. So here is one of the beautiful ASO 3-meter snow depth maps in part of the Northern Wind River Range. And you can see, that's a very clear wind drift signal. Every little rock, every little cliff face has its own little downwind drift accumulation zone. And then here's another example of just some kilometer scale drifts on the leeward sides of these ridges and high peneplain remnants where it's drifting into these leeward cirques. So now our question was, can we model this and kind of extrapolate it over the whole landscape to explain the variations in stream flow patterns? And to do this, we used the Winchell wind model, which uses the upwind max slope for shelter, as well as a flow separation or break and slope index to identify likely drift zones based on a wind direction and the topography. Using that, we created some principal component model of terrain shelter indices and did a Bayesian probabilistic regression against the ASO SWE maps to identify areas of heavy snow accumulation or heavy snow drifting based on these terrain metrics. Here's the result of that. And I'll just give you a moment to kind of look at the agreement of those patterns. What we're seeing is the blue areas are areas where ASO mapped snow or SWE depths greater than 1/2 meter. And the yellow areas are areas that we predict to be drift zones based entirely on characteristics of the DEM. So in other words, we can pretty well identify the spatial distribution of deep snow areas in the Wind River Range entirely based on terrain aspects and a wind direction. Just to extend this a little, we looked at snow persistence in late summer using Landsat NDSI for snow cover and modeled the snow persistence probability over the whole domain. What this is really interesting for is that it shows that the deep snow areas are also the most persistent. And that sounds kind of obvious, but it doesn't necessarily have to be true. That it's not just like the shaded areas or something that are persisting, but it actually is these large wind drifted areas that are persisting. So these two flashing maps here, one is showing the agreement of the Landsat NDSI snow cover that's on the right with the terrain metric, and the other is showing the agreement of ASO with the same terrain metric. So basically the same terrain shelter metrics can model both the late summer snow persistence and the spring snow depth. To tie it all back to stream flow, you can see in some basins like Dinwiddie Creek on the left, there is very high snow persistence, lots of drift zones. Some basins like South Fork Little Wind River, there's hardly any drift zones. And then if you compare the hydrographs for those basins, the basin with the large drift zones is again overproducing that late summer stream flow. To bring this all out to a bigger picture physical understanding of what's going on with all of these different processes, I'm proposing this kind of giant multi-temporal feedback cycle, where if we start with some wind sheltered terrain, like a cirque or some mountain ridges, then in the wind shadow of that terrain, we'll have reduced sublimation because there's less blowing snow. It's just being consolidated into these drifts and not blowing away. And we'll have that increased drifting. And those drifts will lead to a really persistent snowpack in those sheltered areas. If we have a sufficiently persistent snowpack that lasts for multiple years, we can eventually grow a glacier over the hundreds to thousands of years timescales. Now, over the thousands to tens of thousands to hundreds of thousands of year timescales, these glaciers will actually deepen the cirques and steepen the ridges and sharpen the topography in the areas with the most persistent snowpack. So what I'm proposing is this very multi-temporal feedback cycle between wind sheltered terrain, persistent snow drifts, and glaciation. And what this all means for stream flow is that all of the processes combining in that feedback cycle over many, 100,000 year timescale, all can combine to explain the stream flow on the daily to yearly timescale. With increased drifting, lower sublimation, and direct glacial ablation, we get more summer stream flow from the basins with the most wind sheltered terrain. Now to bring this all back to the local scale and what it means for the actual Wind River region, there's huge implications for the resiliency of local agricultural communities. Unlike a lot of the Sierra basins where we have huge reservoirs, the artificial storage in the Wind River watershed is only capable of holding a couple weeks of irrigation water. And so agriculture is entirely dependent on diversion of this sustained July, August, and even September stream flow from the mountains. So the resiliency of these runoff patterns is really important as we move forward with climate change. The good news is that the drift zones are likely to outlast the retreat of the glaciers. If the water were just coming from glacial ablation, then when you lose that ice, you lose maybe your summer stream flow. But if it's a drift zone, you might still have some of this persistent seasonal snow even as the glaciers retreat. The flip side of the coin is the variation between basins might increase with earlier snowmelt and with a change to a more rain-dominated environment or with lower wind speed with climate change, you could lose some of these drift storage patterns. Just as a teaser for our next steps, we're looking at creating some of these probability of snow persistence curves as a fraction of catchment area based on the Planet Labs time series, installing new string gauges to extend this to more watersheds, constrain other storage fluxes, and continue with our stakeholder outreach and management scenarios. but most of all, looking forward to continued ASO acquisitions and making the most of the way we can manage the water in the West. If there's one takeaway, it would just be that the ASO snow maps are helping once again to untangle the cryospheric storage processes driving water supply resiliency. And thank you for listening. I'd be happy to take any questions.
Awesome. Great job, Eli. A lot of cool stuff buried in there. Let's see, Matt Meadows has a sort of question comment. Matt, do you want to ask that or should I read it? Which he can't talk to answer my question. Where'd he go?
Is he still on?
Looks like it looks like Matt has departed. He's asking if this is a good spot for stable isotope water source partitioning.
Yeah, so people have done some
isotopes. Yeah.
Some people have done some isotope studies on the Wind River Range. All of the ones I've seen so far have had really high uncertainty in the glacier versus snow versus seasonal rain partitioning. With the change in the isotopes in the snow in the different times of year, often their error bars end up kind of overlapping to where it's very unclear how much of the total contribution is actually coming from the glaciers, and it could be, kind of orders of magnitude different. So I'm not a very much an isotope hydrology expert myself, but the literature I have seen on it has kind of left me feeling like there's a lot of uncertainty in that approach in this particular case.
I think we have a question from Gus.
Hey Eli, thanks for the presentation. Really interesting. I'm wondering, so just to confirm what you're finding, the deposition that's largely driven by sort of this transcontinental, meaning across the continental divide transport of snow? That's my first question. Then I've got a
yeah, I think so. I think are you asking, like, would this be different on the west side of the divide? Like if we go back out to the map, I'm only focusing on these east side basins. So like, yes, the west side of the divide, I do believe would have very different snow deposition patterns. We actually see that in the ASO SWE map here. Well, it's kind of too small to see. Anyway, it does seem to be very much less drift dominated on the west side of the divide. So, I don't have any direct evidence for like that trans divide transport, but I do see a big shift where these eastern basins I'm studying are very drift dominated, and the west side of the divide, like Green River watershed over here, is much more kind of homogeneous, kind of Sierra looking snow.
Right. Yeah. I guess it's just getting at the original source. So if we feel like the west side of the divide is actually the source for a lot of the drifting that ends up on the east side of the divide, I understand the study's focused on the east side. I'm just wondering about the source of the original source of the snow.
Right. Yes. I haven't really thought a lot about, like, is the snow in a particular drift only being drifted off that mountaintop, or is it being blown, multiple miles of aerial transport? My guess would be that you're not probably getting, 10-mile aerial transport of most of the snow, just because the sublimation losses for airborne snow are so high that once it's truly airborne, I don't think it's probably being transported, a really long way. But I don't really have any direct evidence to support that yet.
Right. Thank you. That was the second part of my question, was about sublimation. So thanks for addressing that.
Thanks for the questions.
Pat, you got a question?
Hey, Eli, congratulations again on your magnificent feat.
Oh, thanks.
And you didn't have to discharge your AK-47, I assume.
Luckily, no grizzly bears quite that close.
Excellent. Just kind of speculating here, there seems to be some nexus between having wind transport and having some facility where the snow can accumulate behind them. And then you were drawing some inference that could lead to creation of glaciers. There's only a couple of glaciers in California. I think there's a couple in Yosemite National Park. Do they meet that sort of criteria where they're wind sheltered and snow transport from wind?
So to be fully honest, I really have not looked at the California glaciers at all. So I'd be totally speculating. But my guess would be that in these high alpine basins where there's just kind of these small glacial remnants, probably yes. I feel like, I mean, again, I'm not a glaciologist, but it seems like the trajectory for these glaciers that are just, very small remnants, they basically end up being kind of just essentially glorified drifts. I'm thinking of like St. Mary's Glacier in Colorado, which is like it's not really a glacier anymore. It's basically just a big ice patch that's caused by this wind drift. So I think where you have these tiny alpine glaciers that somehow manage to survive even after the major glaciers that carved the valleys are long gone, there's got to be some sort of drift, mechanism driving that beyond just a climate mechanism. Because if it were just an altitude and lapse rate sort of mechanism, then why wouldn't there be a lot more bigger glaciers everywhere?
Great, thanks.
Great stuff. Thanks, Eli. Really good work, and looking forward to seeing where you take it.
Thanks so much.
Next up, we've got Dr. Rosemary Carroll, who actually is from the Desert Research Institute. Sorry, Adrian and Eli for broadly applying the designator, too broadly applying that earlier. Rosemary and I have worked together for quite some time down here in Colorado. And she does a great job integrating lots of mountain hydrology stuff with ASO work. So looking forward to seeing what you got for us, Ro.
You got it. Thank you, Jeff. And for Eli, that presentation was absolutely wonderful. So I get to follow that. So yay for me. But I'm going to talk about stream water sourcing to mountain streams. I'm going to talk a little bit about integrated hydrologic models and incorporating ASO into these models. I did talk a little bit about this last year. And so I'm going to kind of just spend a little bit of time on that, but then move into what's been developed more recently. And so just to kind of talk a little bit about the field site. The field site's the East River, which is located near Crested Butte, Colorado. I live in Crested Butte, but more importantly, it's also the field test bed for the Lawrence Berkeley National Laboratories Watershed Function Scientific Focus Area. So that really doesn't roll off the tongue, but SFA for short. And the grand challenge question here is to try to understand and predict how these mountainous watersheds retain and release water and solutes across a variety of both time scales and spatial scales. And so the work my work that I'm talking about today sort of folds into this larger research program. And just to highlight too that the East River is a main tributary to the Gunnison, and the Gunnison in of itself is a major tributary to the Colorado River. And we all know that the Colorado River is under tremendous strain. So there's a lot of opportunity here to sort of begin linking in sort of scientific research and sort of water management scenarios and trying to think about these problems in the mountain systems. So integrated hydrologic models, I use GSFlow. This is a USGS code, and it allows me to capture these complex hydrologic feedbacks across various subcomponents within the watershed itself. So I can sort of monitor the water budget through the canopy, down through the soil zone, and then also down into the deep bedrock system. So often you'll hear us call this the critical zone, but that's what they mean, canopy down to bedrock. So the domain that I'm modeling is the entire Huck 10 level. So it's 750 square kilometers with nearly 2 kilometers in vertical relief. I am modeling at the 100-meter grid resolution, so it's pretty high resolution and a daily time step. And the model runs over multiple decades. It runs from water year 1987 through 2021. In fact, I just ran this last water year too. I'll get to that later in this presentation, but I have some preliminary results from 2022 as well. There's a lot of data that's been collected as part of the SFA, as well as part of various collaborations from local, state, and national agencies and other national labs and university partners. So What I'm going to focus on, though, of course, is a lidar-derived SWE product. This is not just a fantastic product to look at. They're beautiful pictures, but is incredibly important in this basin where precipitation is just a dominant driver in terms of stream flow generation. There are 15 stream gauges in the basin, and all of them are part of the model, and I do a validation on that, but I'm going to just focus on the Almont stream gauge. So just direct your attention. That's the last stream gauge exiting from the watershed. So last year I talked about how I incorporated ASO into the model. So I use a wet water year. So I'll just do it briefly here, but I just use a wet water year where I have a lot of spatial coverage across the basin. And that is sort of trains the GS flow. GS flow does not do wind redistribution. Thinking about the Wind River range, does not do that. Doesn't do avalanches. I don't have a complex model in this integrated model. So I need to trick it, so to speak. And I trick it with a 2019 ASO flight, and then all our other flights just turn into validation. So I'm going to show just one water year here. 2018, this is a very dry year, so it's the opposite of what it was trained on. And just highlighting on the right-hand side that the model at sort of the basin scale, we're capturing some of the nuances in snow distribution, with ASO is on the top and the model prediction is at the bottom, has a relative root mean squared error of about 6.5%. But some of the key features here is that we're getting deep snowpack shown here in red along the Ruby Range, which is on that sort of western slope. This is indicative of that storm patterns coming across moving from west to east. And then we also are getting snow up in these mountain ranges at the sort of northern portions of the model. But if you dive into the upper portions of the East River, you also see the ASO here is at 50-meter resolution and the model is at the 100-meter resolution. But even in this validation set, we're getting that deep snowpack on the northeast aspects in the model. We're simulating those ridge effects. So we're moving snow essentially off the ridges implicitly within the model and putting that deep snowpack on those northeast aspects. And of course, this becomes important for estimating seasonal stream flow, especially from some of these upper tributaries. So what is new? So now I'm going to go into what's new. The new thing that I have is the deep groundwater. And so I have built up a groundwater model down to 400 meters. It seems excessive, I know, but I want to be able to try to understand where is the bottom of the watershed. And so I've got this very deep model, and maybe later I'll truncate it up to say 100 meters or something. But right now it's very, very deep. It has 8 hydrostratigraphic units in it, from tertiary granite diorite all the way up to, or down to, I guess, Permian sedimentary layers like the Gothic and Maroon Formation. So this is a big honking groundwater model. And on the right-hand side of your screen, this is depth to groundwater. So the red areas are where we're getting groundwater daylighting at the land surface. So what I point out is that red signifies that groundwater is discharging into those sort of topographic lows. So those are groundwater to streams. And it really matches up well with the NHD classification of perennial streams. So this was not an easy task. I'm kind of pretty proud of this. I have stream flow being generated from groundwater up in like the Cement Creek area, if you're familiar with that, or the Brush Creek area. So I'm able to get that perennial expression in the model. So I'm going to kind of walk through the water budget. And the very top corner there is the various SWE traces for the various water years that I am simulating. And you can see immediately if there's tremendous variability. We have very, very wet years like 1995, and we have very, very dry years like 2012, and a wide range of scenarios in between. But overall, this system is operating in what I call energy limited. It's wet, it's cold. It has more precipitation coming into the basin than the atmospheric demand. Nonetheless, more than 50% of the water is estimated to leave the basin through evapotranspiration. So getting back to Adrian's talk, right? Like trees matter, right? They use a lot of water, and that's a good thing, but they use a lot of water even in this very cold and relatively wet watershed. And in fact, we see this coming out primarily through the soil zone, and it's through that forested subalpine. We can think of the soil zone as really this arbiter of where and having this very responsive, it's very responsive to that year's climate, that year's snowpack. So the soil is going to kind of arbitrate whether that water that goes in, infiltrates into the soil is going to go to ET, or if it's going to move laterally through the soil zone as interflow. Now that interflow can move and support down gradient ET, it can support down gradient recharge, or it can support stream flow. If you look at the little graphs at the bottom of your slide, these are graphs of potential ET to precipitation against PET to precipitation. So PET to precipitation is aridity. That's atmospheric demand divided by precipitation inputs. And if that value is under 1, we call that system energy limited. So it has more water than it really needs. And if it's over 1, it's water limited. It doesn't have enough water. So on average, 2006 is sort of an averagey water year. That's where we're using ET at about 50, 55, 56%. What's interesting here is on a dry water year like 2012 or 2018, we are water limited, and nearly 80% of incoming precipitation now is going to ET. If we look at interflow to streams on the other side of the, on the other graph, what you're seeing here is it decreases with aridity. So as you get warmer and drier, the precipitation preferentially will partition to ET, and you get less going to stream flow. So I think we can understand that. And that's where all that seasonality comes into play. Now, the last point I want to make about the water budget is groundwater has a little bit more complex sort of routing scheme through it. But groundwater is contributing, by the time you get to the Almont gauge, nearly 50% of the annual export water. So it is significant. And I'm going to just mention in the next couple of slides, we're going to see it's relatively stable as well. So this is the simulated hydrograph in comparison to observed data for that Almont stream gauge. And so this is 34 years. Model's not perfect. There's definitely some more tweaking I need to do on this, but it has a very good Nash Sutcliffe efficiency of 0.87. So for this preliminary analysis, I think it's fairly good. And so we can start to look at the sort of end member water years in this basin. So as I mentioned before, 1995 is the wettest and coldest year on record. 2006 is an average water year. And then 2012 represents one of the driest water years. And I'm providing at the bottom of your slide precipitation inputs. I'm providing stream flow exports and also the amount of stream flow that's exiting as groundwater. So a couple points here. Big water years produce more stream flow, and the efficiency or the ratio of stream flow to precipitation is high. So it's 54%. In contrast, on a dry water year where we have less than 50% of the incoming precipitation, stream flow is 42,000 acre feet, and its efficiency, its ratio is lower than on a wet year, it's 37%. The other key point here is that groundwater is about 37,000 acre feet per year, and down to 32 on the driest year, but it's relatively stable in comparison to that interflow component. But the ratio of groundwater to total stream flow is highly variable as a function of that interflow. So groundwater proportionately on a wet year is much lower than it is on a dry year. On a dry year, it can be as much as 78% of that exiting stream flow. So we have new flights in 2002, and I have not been able to really process this information in terms of how well the model is doing. But I did take liberties this weekend. I ran the model and I started looking at where does the water go? So what, for instance, and again, none of this has been validated, none of this has been tested, but I thought I'd throw this out here. So to be able to talk about it, I took 2 sub-basins within the East River. I took the upper East River down to Pump House. This is an area of about 85 square kilometers. The SWE estimate from our April ASO flight was about 30,000 acre feet. And then Cement Creek, which is a little bit more south. It has slightly larger area. It had only about 20,000 acre feet per year. If you look at the total water budget for up through this past weekend, normalized by area, we look at Pump House versus Cement. We see that Pump House is got more water. It's a colder basin, and it has an efficiency of 60%, meaning that 60% of its precipitation this year is estimated to have left that subbasin as stream flow. 35% was consumed by evapotranspiration, and some of the water actually went into storage, into recharge. In Cement Creek, this is a drier basin. lower angle, less topography in this basin, has less precip, but more of that precip is going to ET, 52%, and less of that is going to stream flow, 46%. We can actually look at then the ratios of interflow, that fast response flow through the soil zone versus groundwater. And we see that Cement Creek has less stream flow, has lower groundwater flow, but a greater fraction of its stream flow is groundwater derived. So the take home here is that we're using these integrated hydrologic models to try to understand water budgets across these mountain landscapes. And ASO has just become a really important component of that to both inform these models, but also to test and make sure that we're getting snow in the right portions of the watershed, especially in these basins that are so dependent on precipitation and or aridity. And these are just very important in terms of predicting stream flow. On average, just wanted to point out that ET in this basin is estimated to use more than 50% of the incoming inputs, and on dry water years can use up to and over 80% of that incoming water. Stream flow efficiency is highly variable, ranging from 37% to 54% of incoming precipitation, with those dry water years really at the lower end of stream flow efficiency, as that precipitation preferentially partitions to ET. And then groundwater is an important water source in our streams, averaging nearly 50%. And while the fraction of groundwater is highly variable because it is a function really of that interflow, which is tightly coupled to incoming precipitation. And at last, I have at the subscales, and I didn't have time to talk about the within basin or between the different catchment variability, but water routing is not universal, of course, across the basin. I showed just sort of hand waved my way across the Upper East and Cement Creek, but topography is a very important control here. Vegetation type and the density is also important. And then we start looking at bedrock lithology, not just on the year of that snow event, but in subsequent years. The memory of that system is really dependent on the lithology. And so that's something else that I'm exploring at the moment. And with that, if there's time, I will take any questions.
Awesome. Thank you, Rosemary. Really cool stuff. You actually, in your last bullet there, hit on what I was going to ask about. And that is, if you think kind of from precip down to snowpack to soil moisture and groundwater, you've kind of got these increasing lag times or residence times of water in each of them, and you've got a long time series of your model.
Mm-hmm.
How does the sequencing of different years kind of factor into these various efficiencies? You know, simplistically, dry year following a wet year, or vice versa, or even aggregating more than just 2 years.
Well, I didn't show these slides in the interest of time, but so what I did to try to simplify the analysis, Jeff, was I started with the same initial condition, first of all, and then I ran 1995, I ran 2006, and I ran 2012. Then I ran an average year after them, just to simplify that analysis so I didn't have to try to take into effect other conditions. So what ends up happening is, and I looked at this basin-wide, I looked at it across elevation, and I also looked at it at the HUP 12 level to see who was responding more, who had most memory, by who I mean the basins. But simplistically, what ends up happening at the basin scale at the entire East River is if you have a dry year like 2012, and then you have an average year after it, you're going to experience, according to this model, a 20% decline in stream flow from what you would expect if you had an average year followed by an average year. So you're going to have about a 20% loss in stream flow. Now that loss is coming because we create all this groundwater recharge in the upper elevations. It moves down gradient either through the soil zone or the groundwater system into the subalpine. And you end up losing all that in the lower subalpine, especially, you end up seeing the greatest effect of that storage loss the following year. You see your largest stream flow declines in the lower subalpine. And you don't see as much in the montane area, just it's already water limited in general. So the lower subalpine gets kind of hammered after the drought. It's what has the most memory. But a 20% decline is significant. And it's coming through a mix of both soil loss as well as groundwater loss. The upper portion of the model in the alpine and the upper subalpine even a little bit, they don't have a lot of memory. They don't have a lot of storage. They suffer lost storage from the year of the perturbation, but then they kind of fill back up. They just don't have that much storage. So it's really down in the subalpine that we start to see issues. Now, in terms of, I've talked to you about this before, but something that really interests me is I ran this model 2006 over and over and over again, because I was trying to spin it up on an average water year and put it in an average condition. And, you know, my model just slowly drained. And I'm like, is there something wrong with my model? Or is it the fact that an average year run over and over again is not enough? You have to have an occasional big year to reset the system and get it back up into. So average year run over and over again is not the same as running a frequency of different events that sum up to the average.
Right. Awesome.
Yeah.
Yeah, that seems super important. The average will not save us.
The average is not going to save us now.
Gus has a question.
Thank you, Rosemary. Great presentation. I'm wondering, you talked a little bit about using the ASO derived SWE data in your model. I'm wondering if you could comment at all on like how much of a difference the stream, you know, the total runoff outcomes in that basin for the years you have ASO data were different from what you were just, you know, modeling without the ASO data.
Right. So the first thing I haven't done like, so originally I was using Prism, just so you know, and this is not supposed to be a diss on Prism, but Prism puts a bunch of snow on the eastern side of the domain. In the northeast side, those are the highest mountains in a way, and it's just, there's not a lot of information. There's a few snowtail sites here. So Prism puts a bunch of snow over on the east, and ASO actually puts it on the west, on those mountains. The effect, by the time you get, if I use the same methodology, the effect tends to wash out, not completely, tends to wash out by the time I get to the bottom of the Huck 12. But what it does is with Prism, I overpredict all my streams on the eastern side of the model, and I underpredict all my streams on the western side of the model. And it's not just stream flow, it's ET2. So the whole water budget changes at the subcatchment, sub-basin scale. And then it kind of, because of the way I was doing it, I was maintaining the same amount of precipitation, but the Prism totally distributed it in the wrong portions of the basin. What I have played some numerical games where I said, okay, what if I just made the whole basin treat it just like 1 point, and I give it the average snow and the average temperature of that day, and I have no spatial distribution at all. It's just treat it like one data point, like if you're going to do a global model or something. And it completely changes the water balance if you do that. You'd have to recalibrate the model completely because you tend to totally change how the water budget is moved through the system. So topography is a big explainer of water movement also in this basin. So if you take away the mountains and you make it flat and put but anyway, so Prism is the only thing I've really tested it against.
I see. Thank you for that. And just one more comment on the groundwater portion. So when you ran the 2006, you said you ran it over and over as like an average condition. Did you eventually, when you said you dried things out, I assume you eventually saw a depletion in the groundwater component as well?
Yep.
Okay.
In fact, that's what I was tracking. So I was tracking the groundwater, and the groundwater is just slowly, it's not quick, but it's just slowly decaying. And it could be this is a preliminary model, but I thought it was very interesting because I was trying to spin up the model and it just wasn't spinning up, you know? And so I was like, average condition repeat. And 2006 is literally as average as you can get. It's not perfect, but it has the closest in terms of anomaly, precipitation. It's got the zeroest anomaly for average, not average, maximum daily temperature, minimum daily temperature. So it does pretty good. And it just, the system starts to unravel, the groundwater system starts to unravel if you just run average over and over again, highlighting that I need to start to look at, you know, how often do you need a big water year? How often is that an important component in the system, even these wet and cold systems?
I think that's a really cool question, because it's not just a kind of a typical climate change scenario approach where you're looking at an average state some 30 years in the future, but you're looking at that sequencing. And we'll still get big years in a changed climate, but are they frequent enough to satisfy those system needs? That's a really, I think, a really cool question.
Another thing that I looked at that I didn't have time, I haven't really ironed out the story, is I started running droughts through the system. So dry droughts versus cool droughts, and increasing those temperature, increasing those losses in stream flow, or losses in snowpack or precipitation. And, you know, the response is not systematically the same everywhere. So some of the upper tributaries actually increased warming, actually increased the minimum daily discharge, but the basin as a whole just loses out big time with warming. But some of these smaller tributaries actually do slightly better, but the basin as a whole does not do better.
Snow refugia.
Yes.
Yeah.
Yeah.
This is great. We have eaten into our discussion time, but I think we're already discussing here. So I'd like to just kind of keep that going. And I also see a couple synergies evolving between what we're talking about just now and this kind of spatial distribution of snow in the landscape and variability in years at ET, and the forest and snow dynamics that Adrian was talking about and presenting on earlier. Adrian, anything come to your mind as we're discussing this kind of sequencing and the ET fraction of these this particular energy limited watershed? How does that tie into the kind of things that your group's looking at in Sagen and elsewhere?
Yeah, it's a fascinating presentation. It's really cool, Ro. Great job wrestling that giant model.
Thank you.
I think the Colorado and the Sierras are different in some ways. The Sierras sort of have a flood management aspect that sort of elicits some different implications. But I do think the question of how forest management translates into peak flows and groundwater recharge and sort of the downstream implications. In the Sierras, we get these big rain events. So it's a little bit of a different animal than having sort of really big orographic, snow events. But I guess, to kick it to Ro, I mean, what are the implications? I know that forest management is now a topic in the East River, based on what you're seeing for like where the recharge areas are. I mean, on one hand, ET is a big part of the water budget, but can you manage that ET with forest management? Is that what the model suggests that?
Yeah, it does. So I didn't show these slides either for time's sake, but if you just look at cross elevation, most of the stream generation is coming in the subalpine, right? And it's coming through that soil water, and then groundwater contributions grow as you go down elevation, which kind of makes conceptual sense. But yeah, the stream is being generated in the subalpine, and so that's where the forest is. Now the scale of that change, I'm not sure yet. If it just gets, my model isn't, as you know, is not it's not a dynamic ecological sort of model, so it's pretty simple. So I'm just not sure what that scale would be, Adrian. The SFA, as you might know, it's moving toward overlap with management of forests, and I'm on the Upper Gunnison River Water Conservancy District Board, and I saw Bev, I think, was on here too somewhere, but is really sort of starting to look at how does water management and forest management, what are the nexus of those two things together, and can you manage together? And so picking the right metrics is a really important and difficult thing to do. And so I think that's something of discussion that would be really great, is what are the metrics for forest/water management that need to be addressed?
Liz, I see you got your hand up.
Yeah, I'm so glad you're both bringing up this topic. And as a forest ecologist, I'll jump in and say, you know, so much of thinking about forest management has everything to do with the role that fire plays in forests, of course, too, right? And how well different forest types are adapted to fire. In the Sierra, in the mid elevations, of course, fire plays more of a role. It's more frequent in forest, and that relationship, that adaptation with fire creates the, you know, that LIGO patterns when we use LiDAR to map forest patterns, the individual clumps and openings that Adrian was discussing. And of course, in some intermountain west forests, you know, the more lodgepole, we're dealing with, of course, the role of fire, not creating clumps and gaps and openings, but of course, completely setting the seral stage of the forest back to the very beginning, right? Completely just having a forest be starting over from the beginning. So I think when we're thinking about the relationships that Rosemary, that was such a great talk, and I really appreciate all the you know, the important illustrations too, with thinking about whether we're colder and energy limited versus, you know, the different types of energy budgets. That relationship is very tightly related to fire as well. And so thinking through these questions, I think, is so paramount to thinking about how we can carry out forest management, how we can think about water budgets. And the one thing I wanted to mention, I really liked Eli's talk, is one of the things that we're even hearing from forest managers in the Sierra is with climate change, we're getting much more frequent wind events. And these wind events are having profound implications for reshaping forests. No, I mean, not to the scale of fire, of course, but they are playing more of a role. So things are changing quickly, and how and what our forests are going to look like in the very near future is going to have everything to do with how much persistence of snow we have on the ground. And I'll stop there.
Yeah, lots of feedbacks to consider here. I'll pause for a second and note that Ken Hurst-Williams will be talking tomorrow, who's also involved in the East River SFA, and he's going to be talking, at least in part, about some of the prospective forest treatment work to be done in the Taylor River nearby the east there. So a bit of a tie-in tomorrow as well on that topic. Matt Meadows, you're typing a question. Are you available to ask it?
And I see Gus has his hand up.
I thought I put it down. I'm good. Thank you.
Yeah.
I was just going to say that last year we spoke a little bit about water deficit and its impact of groundwater and soil water on huge scales, like basically all of the ASO flown basins in California. You know, a lot of times we go, oh, delta S, that's going to be the same from year to year, and we're going to have this base flow. But if you're running an average year over and over and over again, and you're drying up your storage, you're obviously started to look at, well, are my inputs right? But could it be that you're having a long-term problem and that you're actually are going to have it a lot drier? Is your average reducing? I don't know how long your record is, but I know that, like, if you look at some of the long records in some of these rivers, you can't just say from 1895 to present, like in the Kings, my average is this because it goes up and down.
I don't know if that was for me, Matthew, but my first thought is always there's something wrong with my model. That's just, the model is a model and it's got a lot of assumptions in it. And so that's why I haven't yet presented anything there, because I'm still diving into, is the model, like, am I getting something wrong here? But I think it's an interesting thought experiment, and how I want to try to tailor some of my next experiments was, what is average, and does average even mean anything? And I brought this up many times, so if I've repeated myself, I apologize, but Jeff, this is you that said this at something here in Crested Butte. You were like, it's got 100 centimeters of water coming in, that's the average. But that's not the same as 9 years with no water and 1,000 years of water in the last year. Like, those are two different things. And so representing the average is not a great thing. But I don't know, I have to still explore the model. The model is provisional, so I don't think the model is perfect. But
and
yeah,
I think if you have a decade or two of lower than average or above average precipitation or temperature or whatever it might be, that's going to start changing your vegetation in a way that you might not think it's going to change, or faster than science is telling us. I've seen a lot of stuff about vegetation moving a lot faster than they had originally predicted. And now that people are talking about, relocating seed outside of the typical seed zones for forests, just to help the trees move along.
So help a remote sensing geophysicist here. I'm sorry for this question, but like the timescales of latency or lag that are inherent in the groundwater versus the latency lag of the vegetation response, are those comparable here, or are those timescales or their orders of magnitude different? I mean, I'm asking a silly question. What responds first?
That's
an awesome question.
I mean, obviously they're related, right? Because the trees are drinking the water, but I'm just curious.
In my work so far, Joe, we did some age tracing data in Copper Creek, which is a very high elevation tributary to the east. And we got using these techniques, we found that the base flow was around 10 to 12 years old. And that's not old compared to some big giant alluvial basin, but for a mountain system, I was expecting it to be 2 or 3 years old. And so it was older than I expected. And I expect it's going to get, now I've done a bunch of particle tracking through the model. And so this larger model. And so as you move down to Almont, and like, if you're familiar with the area, there's an area called Alkali Creek and there's Roaring Judy. These tend to have very old flow paths. They're very water limited in relative terms, and it's just the groundwater flow paths are longer and older. I just don't have any data to back that up.
But it sounds like the 10-year time frame that you're talking about high up in this one place. To me, that's a lot faster than changing all the vegetation cover.
Exactly. Exactly. So that's
but they might overlap in other places where your groundwater is older, the time scales.
And I'm not an ecologist, and Liz, but the vegetation it's built to sustain wet years and dry years. I think the question is at what point do you move past what it's used to in terms of permeabilities, perturbations from year to year. Like, it's used to a dry year and a wet year, and it's used to that. But at some point it can't take those dry years year after year. I don't know what that is though, what that time scale is.
I think we're getting a sense of that with some of the mortality events, the mass mortality events we've been witnessing. And it's a really good point. We're seeing, trees die very possibly not just due to forest management challenges and fire severity, but it could be that we just start to see a lot of hydraulic failure in trees. And that is a significant concern. And I think that you bring up a really important point about, what is the latency in terms of the timing with the available water, and what if the trends that we're seeing in drought responses is even more delayed than we think. So potentially the dry years that have been experienced, and the coupling effect that sustained drought has could really have a much more profound impact on forests than we realize, and it could come home to roost quicker than we think. Not to be, I feel like, the Eeyore at the party. Forest. Not that the hydrologists don't bring the gloom and doom to the table too.
I think there's some real important questions there. I mean, the evidence is that the trees are pulling water from very deep, but we don't have a good way to parameterize that. And most of our models treat the rooting depths at like 1 meter, and you really can't make the water balance really work in a lot of ways without doing weird things to the storage. So the trees are getting water from deep. That water is more or less behaving like groundwater in terms of its sort of timescales. So I think this is a big open question of how that water is recharged, and then the connections of the vegetation to that deeper water sources.
And can any of you comment? I know yesterday when the DWR director, forgive me here, her name Carla, when she was talking about the groundwater mapping, is that going to be able to provide some insight in terms of better understanding subsurface conditions in California? Is that mapping occurring in our forested basins? Can anyone share any information about that? Because I think that would really help us address some of these questions.
I know that the SFA in the East River has had some of that airborne electromag work done. Ro, have you looked at that in terms of initializing your groundwater model, or at least constructing the subsurface?
They had resistivity, and I am not a geophysicist, so I have spent some time trying to do the sort of an inverse of resistivity to K, to hydraulic conductivity. Failed miserably at that. One of the things I was trying to do is do sort of a Monte Carlo of spatial distribution of within, subunit geologic heterogeneity and how important that is.
Don't feel bad, because I am a geophysicist, and I stay as far away as I can from airborne EM. I mean,
I'm like, oh, I don't know. And so I do need to sit down with Burke Minsley, who was the lead on that, and try to figure that out. But I just think my model has to get working first, and then we'll introduce more of that complexity later.
Stephen Ho beat me to it, but he linked it in the chat. My understanding was that was not going to be in the mountains, which doesn't really help for the runoff portion.
Yeah, so they're mostly looking at the deep groundwater basins and Central Valley.
I think there's so much complexity to it that having sort of a half space of uniform dirt is a bit of a requirement to get meaningful answers out.
But it does provide a nice dinner with some bacon and cheese.
What would we do without the Central Valley?
That's right.
Chad.
I was just going to add an observation from a conversation a few minutes ago about averages, is that I've plotted the hydrology from 1900-ish to current for several Sierra watersheds, and if you just look at the lower quartiles, they're all declining, and some of them are declining to a statistically significant degree at, the 10.1 P. So it really just stresses to me like an average is really meaningless. we never have an average year anymore. And what does it mean for groundwater, for soil, water, and trees when you have this just boom or bust cycle? So we're clearly moving towards greater volatility in the Sierras. And, that really makes me wonder about, the vegetation and the soils, right? The soils are evolved from the climate conditions and how mismatched, both the vegetation structure might be and the soils are from what's actually happening. So just a data point.
It's an important point. I mean, snow really plays a huge buffering role in that connection, right? Changing the timing and the intensity. So really the fine scale snow processes are probably a link into that. But we still really lack the groundwater aspect.
For me, the best data is any well that's high up in the elevation that actually reaches groundwater. So most of my wells are down in the valley. They're the domestic wells, and all the water ends up there, and it does a good job matching it because it's not that sensitive because all the water ends up in the big valley. So any well that's up high elevation is a bonus for me.
Maybe we see these basins like expand and contract, and that's another thing our hydrologic models don't really do. And that's telling you where the groundwater is. People use LiDAR actually to map that. You can map open water surface. I think there's tools like that are probably more low hanging than these really, really complex geophysical tools that, are so cost prohibitive and hard to build a time series. But again, I'm not a geophysicist, so maybe, those tools are really evolving quickly, but I've yet to see it really translate into modeling sort of scale parameters.
One thing that came up in a couple of different contexts today that I see some overlap in is just the importance of the spatial distribution of the snowpack. And Ro, you were using ASO data in one way to get at that. Adrian, you talked about the impact of different forest cover metrics, and then Eli, you were looking at the wind redistribution and the kind of persistence of that pattern. It seems like there's a synergy there as well. Having spent a lot of time at tree line, I see a lot of wind drifting and forest interaction, and that happens to sit right at that kind of upper edge of the subalpine infiltration zone row that you've identified as being critical to the basin scale hydrology. What do we have enough characterization of that variability? Or obviously ASO gets us partway there, but what do you guys see as kind of the next step of incorporating that, or the needs remaining?
I feel like Eli should handle this. I think that wind in snow models is highly underappreciated. And just course tools like Eli is using really show, the dominance of wind. Wind-blown sublimation, I mean, that's something we don't even try to estimate that, basically. But I like what Ro did, which was to sort of implicitly incorporate that with the ASO data.
And this actually was a question for Eli I had, because what I do is I use 1 year as an it informs the model. And then after that, I always assume the spatial distribution is the same. And the lingering snow will vary based on the inputs, but it's always, the deep snow is always going to be in the same place. So this concept of stability in those wind fields and developing those deep snowpacks, which result in persistent snow, even at a smaller scale, right? Like in some of these smaller tributaries, they're really driving stream flow late in the spring here. do you sense, Eli, like that's going to be something? How do you vary that? If you just change your wind field in your modeling, and do you feel that uncertainty?
Well, thanks for the great but hard questions, everybody. Well, first off, I just want to go back to the forest and drifting thing. I might actually just share this image again here. This is that map of the ASO 3-meter snow depth, showing one of my giant drifts. But over here on this left corner is a forested area. This is forest down in the valley. Interesting thing is, I actually didn't really see much drifting, at least the sort of drifting that we see in the alpine areas, in those forested areas. I think the reason for that is probably that the 3-meter scale is even too coarse to really pick that up. If you're thinking about, like, individual drifts around a tree. Because what I kind of saw, at least in the Wind Rivers, was that the forest was the only kind of homogeneous part, which might not be what we expect, but definitely more homogeneous than these, these giant patterns. Oops, stop showing there. But in terms of like the stability of the patterns, the only kind of way I've been able to address it with just this empirical terrain stuff is doing it at a large enough scale that it's more modeling drift zones rather than any particular drift. I initially tried doing this all at like a meter or less scale because there's really high resolution topography available in the Wind Rivers. You can make some cool maps. But it gets so lost in the weeds trying to model like the shapes of these individual drifts that I think the wind field is itself, even just like within 1 year, the wind field is so variable from one place to another that I mean, like having one wind envelope just didn't work for that. So the only way I kind of got it to work is that if you don't necessarily need every pixel to agree on whether that pixel is snow covered or not, but you just want to match the general pattern of it's generally on this side of the ridge, then using a big enough spatial scale, it was pretty stable year to year, even if it didn't exactly line up with the particular drift in any particular year. But I mean, I think the only way to actually capture those particular drift things would be to somehow force some sort of fluid dynamics model with an actual wind field, which is both computationally impossible and we don't have the data to force that. So.
I've played with a number of different snow models that represent wind at various complexities, and I'm completely dissatisfied with all of them. And I can't tell if it's the model because we don't have the data to drive virtually any of them. I mean, the high resolution wind field in the mountains does not exist as a forcing parameter. And the downscaling it from a coarser scale wind is pretty tough. So the way we've ended up going is just using ASO data as basically stamping the pattern on there, because that incorporates the wind field, the results of the wind drifting. It incorporates avalanche redistribution where it's there. And so I kind of like, I've always been a fan of Adam Winstrel's model, just because it did seem to be kind of this intermediate complexity parameterization that, we know the processes that operate at finer scales, but we can't represent them reliably across a mountain watershed. And so that always seemed to me to be a nice approximation. And Eli, I like what you've done by kind of working backwards to that from the observed pattern. And I think that in a way, this wasn't necessarily your intent going in, but in a way helps to kind of validate that model approach, at least on the one snapshot.
We can give Adrian the credit for talking me out of trying to actually run a fluid dynamics model for the wind field.
And as dad, I need to be careful, but I didn't think he'd get a match like that. All right. So, and there are these places where you think it's the edge of his study area, but no, it's a ridge, and they're just like right on. It's pretty cool, I thought.
I think what those models don't resolve, and it kind of got at Gus's question, and Eli and I were talking about this, is like, what is the fate of the precipitation? You know, how much of it is sublimated? Is it blowing from one side of the divide to the other side of the divide? You're sort of just left with, you know, the final.
And I've thought more about that question since we talked about it too. And it's, I mean, I guess where I ultimately come to it is it's almost like we can't think of it as separate things. Like we can't think of precipitation and windblown snow. It's like there's just multi-phase atmosphere. I mean, the precipitation is blowing as it falls. It lands, it blows back up, then it sublimates and falls out again. I mean, like, what does that even mean? Like, there's no such thing as just like this sheet of snow falls down and then half of it blows to the other side of the mountain.
And here in this part of Wyoming, right? I mean, once it gets in the air, it lands in Nebraska.
But I mean, even as it's falling, you know, even the precipitation itself is this mixed phase flow, I feel like, which is in fact sort of one of the big unsolved problems in fluid dynamics, I believe.
Yeah. So what yeah. So in general, we're talking about fluid dynamics models and things like that. You know, Glenn Liston has a model. And he admits it's not all that sophisticated. You know, if you stand your back with your back to the wind, you're going to look at where the snow goes. And that, but the thing we've noticed, in particular looking at in the Sierra, particularly at Mammoth Mountain, is the wind models do pretty well at figuring out where the scouring occurs. But the transport and the deposition don't. What we've noticed, like with Liston's model, is it carries the snow, the model carries the snow too far. That, you know, if you look, for those at Mammoth, if you look at places like Dave's Run, you know, the scouring occurs on top, and then it, you know, pretty much deposits snow at the top of the run on the lee side. It doesn't carry, in general, the wind doesn't carry it all the way down, but there's a deceleration in the wind when it goes over an obstacle, and so, well, it's just like a snow fence. You know, the deposition is just on the lee side of the snow fence. So
yeah, on the windward side, you have a continuous field, and it is differentiable, but on the lee side, generally we run into those obstacles, and so it becomes far more unstable.
Yeah. The wind is blowing pretty hard here in Mammoth, so I'm going to mute myself again.
And then also just to point out, one of the ways in which I, you know, cheated a little bit is I'm only calibrating this wind model to a binary map. You know, it either is greater than a ½ meter SWE or it isn't. I'm not modeling here it's 2 meters, here it's 1/10 of a meter. It's just kind of drift or no drift. And I felt kind of lucky to get a match on that, but to actually model, you know, here's the really big drift and here's the only slightly big drift, does require even more of that kind of what is the ultimate fate of every snowflake sort of approach.
Liz is asking about using some of the fire modeling wind approaches. And Liz, I and a couple collaborators, and I've seen other people, or actually the Micahs could speak to this as well. There's the Wind Ninja model out there, which is a downscaler. And I tried to use that in conjunction with Glenn Liston's model, actually, Jeff, and ran into all kinds of problems. And we're using an ASO snow depth map to validate things, and it comes down to that there's so many multi-scale processes afoot in wind drifting or in scour and deposit, that you can't really model all of them at a fine resolution. And or at least that was that was my take home. And so it looked like the wind field out of Wind Ninja certainly looked more reasonable. It's accelerating on the compression zones, and it's decelerating in the leaves. But how that maybe it just requires some more tuning of the snow redistribution routines, but we couldn't get it to work.
I mean, one point I would just kind of like to make on all the wind modeling stuff is, I mean, it's fascinating just from a pure science side to try to come up with extremely complex models that accurately capture these sorts of things. I mean, my background is physics, so I'm no stranger to just, you know, fancy models for the sake of modeling fancy processes. But in terms of like implications and water resources and climate change and resiliency and all that sort of stuff, do you think it's enough sometimes to have some of these simpler models that maybe don't do a perfect job, but at least can kind of suggest that, you know, maybe this is a wind process that we're kind of seeing. It's not perfectly replicating it, but it is suggesting that, you know, the funky ASO pattern we see is maybe explainable based on these wind characteristics, and thus we can draw some inferences about how those wind characteristics may or may not be, like, you know, sustainable in the future. Versus trying to just like replace ASO with a fancy enough wind model.
Well, I think yeah, thanks for unmuting me. Just talking on the Wind Ninja thing real quick. Yeah, exactly. That is a operational, essentially fire-based, or at least the initial intent was for firefighters to use it on the ground to be able to predict. You know, use forecasting models, figure out in real time, are we going to have problems based on the dominating wind direction and speeds. We use that in the modeling because it works better than some other models, and it can be run in near real time. It's not a science model. My background is in wind modeling and complex terrain. Those models are incredibly expensive. When I was doing my graduate work, it would be like, I want to run a 9-minute simulation, I'll come back in 9 days. That kind of thing to capture turbulent fluxes. But yeah, I mean, that's kind of the hard thing is, what's the scale that we're doing? What's the time scale that we're trying to operate on? And how does that relate to what's scientifically out there right now? We use the mass solver in Wind Ninja because the momentum solver is too expensive, because even that, it's a pretty basic model, but it's really hard to run in real time or near real time. I don't know that I said anything new there, more just adding back up to what everyone else said.
Sorry, I wanted to throw this up here. This is on the backside of the minarets in the San Joaquin. And the faces of those drifts are about 30 to 45 feet tall. And I want to see you guys model that, because the surface underneath is rather smooth. And this is on the windward side. So anyway,
while we're sharing funky drift pictures, I've got one here, if you don't mind. There, I threw that one. I think I sent this one to you, Tom, like a couple of years ago.
Oh, I hadn't seen that. That's awesome.
There's no like poles that, you know, upwind of that or anything.
Right.
That's just the way it is.
Right. No, it's the aliens communicating.
Yeah, it's snow lines. No, but I mean, what do you think of the idea that kind of like ASO will map the actual snow distribution, and then if we can at least suggest that, you know, maybe this is being, you know, use some simpler models to suggest which processes are maybe driving that, then we can get at the resiliency of those processes without having to worry about, you know, making those drifts look the way they actually look.
I think that is 100% right. That's basically what we're doing now, is we can't model these drifts very well, or we're trying to, but I think we'll get there eventually. Maybe not like that drift that you just showed, but at least we can kind of compensate with ASO data. And that's just incredibly valuable, because yeah, we would be losing a lot of the timing of the snow melt if we weren't updating with ASO data.
Yeah. Well, what they say, you know, good data can outlast bad models.
It's a great saying.
I love it.
One thing that's interesting with the Winchell model is like where that was originally tested in Reynolds Mountain East in Idaho, they found that I think you had to go down to 10-meter resolution on the models for that to actually have a decent correlation with the snowmelt timing. And that really speaks to maybe the drift, Tom, you were just showing. We could probably get it at 50-meter resolution, but yeah, the scale of the drifts obviously matters a ton.
And I'd like to just, we spoke of Adam, I think, at the last workshop, but Adam, he was doing the initial ice snowbow runs for us when the program started. And then he went to Davos to work at the SLF. And we lost him to cancer, what now, 2 years ago? I think it was. But despite being from New Jersey, he always had a smile on his face. He was a great guy.
Yeah, I miss him. I think we are at our time here. I do want to acknowledge a question that Stephen Ho put in asking if we could fly before and after an AR event to quantify exactly how much snow the Tuolumne owes to the Merced. Which I'm not gonna step into those politics there, Stephen, but I like the idea, and that's something that we've talked about before, and we've had some luck in the past to capture individual snowfall events, and really, you know, what we've been talking about is kind of the measuring the state of a snowpack that evolves over a sequence of storms, and California unfortunately provided us with an end member example of that this year, where the bulk of the snowpack that peaked on January 1st in most of the basins was derived from one atmospheric river event. So we were looking at the expression of one snow accumulation event over the landscape rather than the typical, you know, 6 or 7 or 8 or 10 of them from different directions. So that's something I'd like to maybe put a pin in, is looking at that from a scientific perspective primarily, but capturing individual snowfall events, but also dovetailing with other efforts like CW3E and the atmospheric river monitoring, and tying that into the forecast informed reservoir operations in California. There's a great synergy there with ASO snow monitoring as well. So we got to capture. Matt and Stephen are now articulating the economic model to get the snow back into the Merced from the Tuolumne.
So
anyway,
that December event, I had the Tom Painter family invited me over for dinner along with Kat and Rachel, and so I left and I drove Kat and Rachel home, and then I couldn't get to my house because of the snow. And fortunately, I carry a sleeping bag in my car, and so I spent Christmas night in a sleeping bag in my car.
So the moral is never drive Kat and Rachel home. Is that what you're saying?
Yeah, I think
Shoulda just-
that's the moral.
Everybody should have slept on the floor. We would have had a fire and or breakfast or dinner wine and dessert wines.
Yeah. Well, hindsight is always good. So.
Especially when you're stuck in a snowdrift.
Yeah.
Awesome. Well, I want to thank all of our presenters throughout the day, and to everyone who stuck around through the discussion today. This has been awesome. Tom, any parting thoughts going forward?
No, I would ask if for the presenters, if you can send us your slides, at least the slide set that you're comfortable having out there. We're going to try to get these up on the website. Of course, we have the videos as well. But I can say that I, of course, enjoy pilfering from these slides and do so quite liberally. And I just think this again is it's an exciting time, and we're really we just feel really lucky that that we stumbled into all of this back when we did, and that that we have such an amazing community that we get to interact with.
Amen to that. All right, okay. Come back tomorrow, 9:50 a.m. for that's Pacific Daylight Time. And we've got a few modeling and forecasting talks in the morning, and then some more good science stuff on tap. So thanks again, everyone, for today.
Have a good night.
And a very entertaining chat too. Like the chat box is hilarious.
Yeah. Excellent.
Bye.
All right. Thanks, everybody.